Good morning. Today's session begins with the second part of the mini course on combinatorics of plane Kerr singularities of Patrick Popescu-Pampu. Please feel free to stop Patrick if you have any question or remark.
So thank you very much, Evelia. Thank you to you to be here for the second and last part of this mini course. So I'll begin by recalling rapidly what I explained yesterday. So first I spoke about my great Spanish friends, then about my collaborators. I said that this mini course is based on the first chapter of the first volume of the Handbook of Geometry and Topology of Singularities, where we gave all the details, all the proofs are contained there. So if you need to know exact proofs, you may look in that chapter, which is also available in its published form on my web page as a direct access. I recalled what we mean by a plane curve singularity. Then I said that the aim of the mini course is to unify the main trees used in the combinatorial analysis of singularities, which were Kuolu trees, Eggerswald trees, and request diagrams, dual graphs, and splice diagrams, and that this unification will not be done by an algorithm of transformation from one to the other, as is usually done in books, but by embedding them all in a same object, which we call a lotus. And then I showed an example of a lotus, and I began to recall the standard ways to analyze the singularities, first by iteratively blowing up points, giving the example of a semi-cubical parabola and the corresponding dual graph of the final minimal embedded resolution. Then I showed how one is led naturally to the notion of Newton polygon by Newton's method of looking for a solution of an equation y as a series in x. This leads to a problem of minimization on the support of the polynomial, and the minimum is achieved on a compact edge of the Newton polygon. That's the moment when the hero of the story appears, which is a Newton polygon. And then I explained why in this example we have a Newton non-degenerate situation, which means that in fact we can arrive at the minimal embedded resolution by a toric morphism. I made a small pause by showing some historical drawings, and then I explained how the usual fan drawing on the left side here can be transformed in a first example of a lotus here on the right hand side. Then I explained that the lotus is in fact to be thought and drawn as a combinatorial object, so without any precise metric structure here on the left, and that it has a canonical embedding in the affine plane. And sometimes it is useful to think of this embedding and sometimes not. And for instance, if one is interested only in the final dual graph with the self-intersection numbers, only the combinatorial structure matters, because one reads the self-intersection numbers by counting the number of triangles adjacent to each vertex here on the boundary. And then by looking only at the lateral boundary, one gets the final dual graph, but not only with the strict transforms of the curve under study, but also of the axis of coordinates. And I explained that it's very important for understanding all the drawings and to have good correspondences between different objects, to put in the pictures all the axes of coordinates of the charts used in the process of resolution. Then I explained that a fan leads to a toric modification of C2, in which the new surface may have singularities, and that one reads by joining the two generators of the lattice, one can read the dual graph here of the total transform of the initial axis of coordinates, which are separated here and are joined by orbit closures in the toric surface. So combinatorially one can read this just here. Then I explained the general algorithm, which applies also when one is not in the Newton non-degenerate situation, which is simply iterating the previous transform. And at that moment, I explained that the Newton polygon intrinsically depends only on the curves defined by the coordinates x and y, which we call a cross. A cross is simply a germ of normal crossing divisor with two components, but ordered. And this order matters because it allows, when we look at the associated numbers, to differentiate between a number and its inverse. And so the Newton polygon is intrinsically associated to a cross and to a singularity at that point. And because a dual fan leads to a toric morphism, if we fix coordinates, it's natural also to ask what is its invariant meaning. And seen in the toroidal category, this, or if you don't know what that is, think simply analytic category, that modification is dictated by the objects here. It means by L, L prime, and C. So one can arrive at a general algorithm which is non-deterministic because it involves a choice of a smooth branch to complete crosses at several moments, in which first one starts from a smooth branch and a germ on a germ of smooth surface, so L and C. If there L and C form a cross, we stop, and otherwise we complete L by L prime to a cross. Then C has a Newton polygon, a dual fan that gives a toroidal modification. We look at the strict transform of C there, and then we repeat by taking as a new surface the germ of surface on the strict transform. The property of the strict transform is that it does not pass through the singular points of the surface. Therefore, we are again in a smooth setting. L is simply the germ of the exceptional divisor there. We have to complete and to iterate. And I showed this on an example in which one considers the first Newton fan, here a corresponding toroidal modification. There one sees some of the branches of the curve under scrutiny appearing there, forming crosses with the exceptional divisor, but at some other points not. So one has to iterate there by first introducing these new curves, L2 and L3. Then one has again Newton fans here, one repeats, and in my example there is a third and last step. And now one can ask what is a dual graph of the final divisor here. What is a dual graph? In terms of the objects which are computed at each step, it means in terms of the dual fan. And then one simply does the construction with a segment here intersected with the rays several times. So one transforms this into this segment. And one has also to record the slopes appearing here. This is called the trunk of the corresponding Newton modification. So one gets several trunks in this way. These final trunks without intermediate points are the trunks when one stops, of the final crosses, when one does not modify anymore. And then one glues all these trunks simply by identifying points which represent the same curves. And this is very concrete. This is what you can do on the paper when you construct examples. Simply you draw the names near the points and then you glue them. And in our case, one gets a tree which we call the fan tree because it was built from the knowledge of the Newton fans of the process. So the fan tree, first here I showed its topology and also the labels which allowed the gluing, but it comes also with numerical decorations which are simply the slopes on the different trunks which were glued. So the slopes in fact increase in this way. One has to imagine that in fact these are special points in which one computes the values of a function which is defined on this segment and establishes a homeomorphism of the segment with the interval 0, infinity. So all these functions glue into a global function defined on this tree with values in 0, infinity, function which has discontinuity points here. It is continuous here, then discontinuous here because it jumps back from c over 5 to 0, and then it increases continuously to infinity. And here, for instance, it is discontinuous. It jumps from 2 over 3 to 0, and then it increases again. This function is important because now, in order to understand other numerical invariants of the singularity, they can be understood resulting from integral calculus on this tree. So this replaces the usual integral interval in which one learns to do analysis in the first year of university for functions on one variable. Here we still have one variable, but on a space with bifurcations on this thing. And you will see that we will have several formula involving integrals on this tree. So this is the first function which is important for integration. That one, and that's why I insist, you do not have to imagine that you decorate only the vertices here with rationals. Those are special values of a function defined everywhere here. So now, first thing, this tree is in fact the dual graph of the final divisor, and the numerical decorations allow to determine which points on the total surface are singular. And I explained that one can do this by looking at neighboring rational numbers, looking at the corresponding determinant, and we get a singular point when the determinant is not plus or minus 1. Then came the question of getting an embedded resolution of C. To get it, one has to resolve the singularities of the previous surface. And then, when we have an embedded resolution, we have the divisor of the total transform of C. And here, a moral is that one has to add to C also all the axes of coordinates. It means the crosses used during the process. And then, in order to see the final dual graph, there one needs to draw a lotus. So this is the moment when appears a lotus. And I explained that instead of drawing here the fan, first, if we want to resolve the singularities, then one has to add new rays to transform it into a regular fan. And there is a minimal way to do this, and we call this the regularized fan. So we ask how we regularize this fan. And the construction is that in each of the cones appearing here, we have 4 of them, we look at all the integral points, and we take the convex hull of them. And the boundary of the convex hull draws this polygonal line here. And if we look at all the integral points on the polygonal line, we get new points. Joining them to the origin, we get the regularized fan. And now we have to change this picture. Instead of drawing rays here, we erase the rays, and we draw inside some triangles. And how do we draw them? It's simply the fact that instead of imagining this first quadrant filled with points, usually, since we are children, we imagine here small squares, because our education was built on this way of filling these points by squares. But here we have to draw something different. We have to draw triangles, and we have to imagine behind this image, in fact, this object, which is a universal lotus, in which we start from this triangle, and each time we extend one of the edges by an equal segment, and we draw a second triangle. So this triangle gives birth to 2 triangles, in turn these to these 2 triangles, and successively in this way. In this way, we do not fill the whole first quadrant, but we get triangles which reach all the primitive integral vectors here inside. That is, all the points whose coordinates are coprime positive integers. And because this has the shape of a flower, inspired by Bernard Tessier more than 10 years ago, I called this a lotus. And therefore, these petals are, these triangles, I call them petals. So you see here you have a lot of petals which are in bijection with the primitive vectors in the first quadrant. And so therefore here, in the previous drawing, one has to imagine that you look at these rays and you take the union of all the petals which are traversed by them till they reach the primitive vectors here. And they are exactly these petals. So this is a lotus associated to these three rays or to these three rational numbers. So now I will explain you. I also showed you yesterday some pictures showing combinatorially this object introduced by Duval in terms of infinite linear points in 1944. And so here you see an extract of the universal lotus in terms of infinite linear points. I stopped here, so now I decelerate, and I will explain you in a slower pace what happens. So what is the problem now? I want to show you, if you have one rational number, how to construct the corresponding lotus combinatorially. So not with its embedding. And it's very important to understand this, that what you should draw is a picture which is correct combinatorially. If you really do the drawing in the plane, very rapidly you saw in the picture before, let's come back here, that the triangles become extremely thin and you see nothing inside them. So you are obliged to deform things metrically in order to be able to look at the combinatorial structure. But because a lotus has a canonical embedding in the plane, you do not have to care about that embedding. It is God-given. So let's come back. And I take the example of this number. Which one exactly? Well, I did not compute it here because what matters is, in fact, the development of a rational number as a continued fraction. There is always a canonical one as a continued fraction in which the last number here is different from 1. In this example, we have 4 partial quotients. So what do? We draw a first triangle here with an oriented base. I said always that lotuses have a privileged edge which is oriented, which I always draw in red like this. Now one decomposes it into 4 triangles. 4 because we have 4 numbers here, by a zigzag line. How? The oriented edge leads you here, so you will start the drawing from this point. So 1, 2, 3, and now you see that you have 4 triangles. And now you subdivide each one of them, starting from here, into as many triangles as indicated by the number. So here you see 3, so I subdivide this one into 3 triangles. Here you see 2, so this second one is subdivided here into 2 triangles. Here I see 1, so this triangle I don't subdivide it at all. It's only 1 triangle. And the last one here is subdivided into 4 because I read 4. So the thing is that abstractly this is a corresponding lotus. So you see, computationally, if you want to know the combinatorial structure of the lotus corresponding to a rational number, just you do this development, which is done simply by performing the Euclidean algorithm, starting from the numerator and the denominator, the algorithm which tells you that the numbers are coprime, but here we already know that they are coprime, so it is not what we want. What we want is to get this structure. And in fact, this structure is a structure which encodes completely the structure of the Euclidean algorithm associated to those numbers. And I will show you some funny facts related to this. But before those funny facts, let's see now how to construct the lotus associated to 2 rational numbers, meaning that, in more geometrical terms, we want to know the lotus associated to a fan with 2 rays. So simply, if you think from the viewpoint of the affine embedding, well, it's the union of the 2 lotuses. But from the abstract viewpoint, you can construct the lotus of each one of these 2 numbers. Here, that which has a development 4, 2, 5, and 3, 2, 1, 4. Each one has a lotus. And now we will do a gluing. And that gluing will identify initial parts here. And what we have to do is to glue the maximal isomorphic sublattices. So what does it mean? Simply you look here, how does this begin? You see that here it begins with 4 triangles which go to the left, meaning that each new triangle is glued on the left of the previous one. And here also we have 4 like this, 1, 2, 3, 4. Visually, you could have the impression that it stops at 3, but it's not the case, because here you see that this is also glued on the left. And now here the next one goes to the right, and here to the left. So here you have this bifurcation. So the common parts are here, you glue them, and you get then the lattice of these 2 numbers. And if you have 3, you keep doing this. So combinatorially, if you begin to try, you will see that it is very rapid. It is as rapid as multiplying 2 numbers, as you learned when you were children. You learned some rules of putting one below the other, then writing the results in diagonal, how to make the sums in columns. There were also graphical rules like this, and once you learned them, you never forgot them. So if you want to learn this, you make 10 exercises, and I think you will never forget how to do it. So now, let's see the opposite. How to reconstruct a rational number from its lattice. So the lattice is simply the simplicial complex. So let's see how to compute the rational number which gives birth to it. The answer is that we simply do Farey addition of fractions. Farey, who was in fact a geologist, published only half page of mathematics at the beginning of the 19th century, and that was enough for leaving its name in mathematics. And there he found a very nice property of the dreamt addition of fractions. Adding fractions for children is always difficult. And Farey addition is what would be the dream world. So simply, you add fractions by adding numerators and denominators. So what do? We start here on the base with the fraction 0 over 1 and 1 over 0. And then, on the first triangle here, you add them in Farey addition. 1 plus 0, 1, 0 plus 1, 1. And then on the second triangle, now you have these 2 numbers on the base. By Farey addition, 1 plus 1, 2, 1 plus 0, 1. Here, 1 plus 2, 3, 1 plus 1, 2. You arrive at 3 over 2. So this is a lattice associated to the cusp, corresponding to the Newton fan dual to the Newton polygon of y2 minus x cubed. And this is what happens in general, exactly like this. Why is it like this? Well, because Farey addition means simply that instead of thinking of the rational number, you are looking at the corresponding vector with 2 coordinates, such that the rational number is a slope of the vector. And then Farey addition is simply the addition of vectors. And I told you that the lattice is constructed each time by replacing 2 vectors by one of them and their sum. So the lattice is constructed exactly by doing sums of vectors which form bases. And this is what we do here. So understood in this way, you see that it is completely obvious. But now something which is not as obvious, and for which, for the moment, we do not know applications in singularity theory, but I feel that they are, and I would be very happy to see what it means, is the following. Is that now on the lattice, individually the 2 numbers 3 and 2 have a combinatorial meaning. Namely, look at the lattice, and now each triangle oriented in the following way. So what we will orient is not the triangle, but its edges. The base of the lattice is already oriented from the beginning. Now, the first petal here, simply we orient it from the new vertex to the base, in this sense and this. And we repeat. From the new vertex, we go to the base here. From the new vertex to the base. In this sense, in this way, the one skeleton of the lattice gets completely oriented. And now you can look at paths which grow from the vertex to the base. And you look, how many paths do I have preserving these orientations to this vertex and to this vertex. And if you look here, you see that as path we have the direct one, and also after doing this we can go this way, we have a second one, and these are the only ones which start in this way, and we can also start in this way. But then from here we have only this solution. So we have totally 3 paths leading from here to here. And if we want to go to A1, well, we have a direct path, and it is the only one which starts in this way. And otherwise, if we start like this, well, we cannot reach here. So we are obliged to go here, and here we have again a solution. So only 2 paths. And so you see that 3 and 2 are exactly the numbers making the numerator and the denominator we just computed. And this is a general property. And for the moment, we do not understand the importance of orienting the edges in this way for singularity theory. I'm convinced that it has an importance somewhere, but still something to understand. So now I arrive at the answer of the question I asked, how to arrive at the dual graph. Remember that the dual graph with its self-intersections is, we saw it in the baby example of the Newton non-degenerate situation, as the boundary of the lattice. So here it will be the same. We will get the dual graph as a boundary of the lattice associated to the toroidal resolution process. And therefore now, instead of gluing trunks, we will turn each trunk into a Newton lattice, and we will glue the Newton lattices in the same way, meaning identifying the points which have the same label. So remember that we have three stages of Newton modification. The first one was governed by one fan with 3 rays. We turned it into a trunk. But now, no. The trunk, we turn it into the corresponding lattice. You could think at this transition direct, like here, if you do what I told. Think here behind at the universal lattice and look at the petals which are crossed by these rays and take their union. Then you get this. But you could also think of the process which I just showed you. By looking at the continued fraction expansions of these numbers, you construct 3 elementary Newton lattices which you glue afterwards. This second description has the advantage of making you understand at which place of the algorithm you need to do continued fraction expansions. It is in order to construct this structure. And we begin to see an advantage of lattices, that the lattices allow you to see the algebraic computations as an algebraic image of the internal structure of the lattice. So here is in fact a picture of the algorithms that you apply. So you do the same for each Newton lattice. So we have in the second stage 2 lattices, and you see again I put the labels of the curves appearing each time. And how do you know them? Well, it is because precisely you know on which curve you were led to add crosses. So this is because you detected there that you have multiple roots. So each time you do this, you add a label there, and you know that at that point you will have to glue another lattice. And the last one is a small one like this. And in particular, pay attention that you get also rational numbers which are here smaller than 1. 1/2 means that we are in the situation exactly like for the semi-cubical parabola, that we get a strict transform which is tangent to the exceptional divisor. And you have to project in that way. This shows that each time you care about resolution of singularities, you do not have to assume that your coordinates are generic. That's why all the papers we did around this project never assume that we are in generic coordinates. Why? Because that genericity hypothesis is not preserved by modifications, be they blow-ups or something else. So this is also something very important. Many times we present our results as a theorem with hypotheses and conclusions. And we do not explain for which global reason we needed those hypotheses. And you see, hypotheses could be chosen in a way which is adapted to some global process. And if we do not say that, we give the impression to the rest of the world that mathematicians play games which have no relation with anything else. And I think in order to change this, one of the things we should change is also to explain why the hypotheses of our results are adapted to big schemes. They are needed somewhere for making some general process work. So here I insist, we never have genericity assumptions on the coordinate systems. So now, just glue by identifying points with same label, and we get the initial lotus I showed at the beginning of yesterday's lecture. So now I think that your eyes are modified. I leave you 10 seconds to look at it and try to see what you see now on it. 10 seconds. Okay. So may I ask you, what do you see in it? Please. There. Please, not Pedro, not Evelia. Please try to say what you begin to see from the process here inside the object. No, nothing, nobody dares? No. So I'm sure that you see a lot of things, but let's tell you what we can see initially. So first, now we got an embedded resolution. So we arrived at a surface which is smooth. And we have, therefore, a modification from a smooth surface to C2. By a theorem of Zariski, this gets decomposed as a sequence of blow-ups of points. But now, each time we blew up a point of intersection of two curves. The curves added perform exactly this role. So initially, we have the curves which are the axes of coordinates. So the origin appears as the origin of the initial cross. The dual graph of the initial cross is this segment going from L to L1. And then, each time we blow up, we draw a triangle. So this first triangle represents the first blow up. And then here, this point represents the first exceptional divisor. The fact that we added a triangle here means that we blew up the point of intersection of the exceptional divisor and the strict transform of the first axis. And also symmetrically here, we blew up the point of intersection of this first exceptional divisor and the other axis. Here, we get a second exceptional divisor, E2, and you see that we blow up again the point of intersection of E2 and the strict transform of L1, and we go here. But we do not blow up the intersection point of E2 and E1, because here we do not see a triangle. So in the way triangles are glued here, you can see at each moment which point was blown up. You see, moreover, that each segment here in the lotus represents a dual graph of an intersection of two curves which intersected sometimes during the process. But at the end, they may not intersect anymore. Look, for instance, here. These two, well, at the end, don't intersect directly because we blew up precisely their intersection point. And the final dual graph is simply this yellow part, which is here. So it is a tree. And in fact, this tree, if you look at it topologically, how it is done, we replaced this segment by this one. But projected from the origin in the corresponding plane, these two are homeomorphic. And in fact, the boundary of the lotus is a tree which is homeomorphic to the fan tree we saw before. And here is the first thing. This tree, constructing using all these ancillary curves, the axis of new coordinates, has the property of being canonically homeomorphic to other trees. And you will see that we will have 4 different trees which are canonically homeomorphic. Each one comes with different numerical decorations coming from its origin, because each tree appears from a different way of analyzing the singularity, and the passage from one numerical decoration to another one is done by doing integral calculus on this tree. So now you can also say, when I blow up each time, you know that I have one chart and I get two new charts. So you can say, well, these internal segments represent all the charts appeared during the resolution process. Initially, I have the chart of coordinates x, y, then u1, u2, v1, v2, and like this. And so when you do the computations in charts, now you can know that you can follow them in the lotus. All the charts can be pictured there. Moreover, I prepare the relation with Enriquez diagram. Enriquez diagram is a tree whose vertices are the points which are blown up, which are called the infinite linear points of the initial point. Those points are in bijection with the exceptional divisors appearing here, meaning all the points on the boundary excepted the blue curves here which were added. How? The bijection is simply you associate to a point the divisor obtained by blowing it up. So it means that you can ask what is the Enriquez diagram related to this structure. And we will see that the Enriquez diagram embeds as a subgraph of the graph you see here. So this is what you can see for the moment. Also the self-intersection numbers, for instance, this vertex here as a self-intersection number. We have 3 triangles, -3. And it is in this way that you can see the self-intersection numbers. So now the dual graph, which appeared as a kind of abstract graph, decorated with numbers, now you know what those numbers measure. They get a topological interpretation. They measure local aspects of this structure. And now, something I told yesterday, you can see in this the space-time evolution of the process of blow-ups or of the resolution by those toroidal modifications, regularized toroidal modifications in order to get at each step a smooth surface. So the initial dual graph was this. After one blow-up, it's this. After the next 2 blow-ups, it arrived here. Then it arrives here. And in this way, you can see it like the sea which comes back to the Earth. It's not horizontal. The sea adapts to the territory in which it extends. And you can see that at the end, you got this global picture. And this is the space-time evolution. The final, the present state is just this yellow boundary. The initial state is just the union of these red edges here. And the intermediate stages, you can see them inside the Newton lotuses. And the fan tree, as I told you, embeds here in the boundary. So remember that I took the convention to draw the segments blue if the corresponding point on the surface, on the toroidal surface, was a singular. So now when you embed it here in the boundary, you see that here the blue ones are exactly those which are subdivided using the vertices of the lotus, which means that there precisely we had to resolve the singularities. So this means here, for instance, for the segment between E1 and E6, which represents this one, that we got a resolution by adding 2 intermediate points, with which self-intersections, -3 and -2. And in this way, on the lotus, you see all the toric singularities which were resolved and in which way they are resolved. And now the very important part, I said that these 3, in order to encode the combinatorics of the situation, of the singularity, needs numerical decorations. But pay attention, here we do not need them. Here we can reconstruct them from the internal structure of the lotus. And this is the difference with all the other objects. The other trees which were used till now were trees, so you can say they are more or less complicated because this is a two-dimensional object. But here, the advantage of passing to this two-dimensional object is that now you have pure topology. It has this simplicial structure, and now you can begin the game of saying each number here represents what from the viewpoint of this object. And now I told you that, for instance, these numbers 5/3 and 3/1, well, here they are on this trunk which goes from E1, E6, E7, infinity. So it corresponds to this Newton lotus. So all of them speak about the internal structure of this part of the big lotus. So now you are able to think topologically about those rational numbers. You can say more than saying one is less than another. Well, they measure different parts of this object. And you can have twice 3/2, but you know now to look. One 3/2 speaks about this, and another 3/2 speaks about this. And this, I think, for me, it's the biggest advantage of topology, as was dreamt by people in the 19th century and by Poincaré. He developed what was called afterwards algebraic topology, and which he called analysis situs, as a way to see things using figures in spaces of arbitrary dimensions. So topology is not a matter of doing computations. It should help doing computations. And our perspective was to explain in which way this object helps doing computations, because now we know that all the numbers and the computations we do travel inside this. And you can see how in your computations you are climbing in the lotus and going in different directions. So now I pass to different direction. Till now we were speaking about resolution by blow-ups or points or by toric modifications. Now let's come back to the initial Newton method. Iterated Newton method leads to power series solutions of the equation f of xy equals 0, which were called Newton-Puiseux series afterwards. Puiseux is a person who studied the convergence of those series and also started the monodromic study of those series. And now if you ask, well, I have the previous lotus. How can I write concretely Newton-Puiseux series whose minimal polynomials define a curve with that lotus? Which means, for instance, you draw a dual graph and you say, well, now I want to write Newton-Puiseux series. What to do? And I think, in general, my answer before was, I know, you have to look in such and such a book. So now I want to show you that by practicing a little, you don't need to look at books anymore, and you do not need to remember algorithms. You have just to look at the lotus, and you will know in a flow how to look at it to write the Newton-Puiseux series. And the answer is that we do not have to jump directly to the Newton-Puiseux series, but first we have to construct from the lotus an associated Egers-Wald tree. So let me explain you what is an Egers-Wald tree. But first, I live in Lille, which is not far from Bruxelles, so this is a kind of reference to Bruxelles. I start by explaining what is not a Newton-Puiseux series. So please think about Magritte. So the first series is not a Newton-Puiseux series. So to young people, why it is not a Newton-Puiseux series? You see, the exponents are the sequence of rational numbers of the form n plus 1 over n. Well, this is not a Newton-Puiseux series because you do not have a common denominator for all those numbers. A Newton-Puiseux series is a formal power series with complex coefficients, with rational exponents, which are positive rational exponents, but with a common denominator. So the second one is a Newton-Puiseux series. Starting from here, I write simply the rationals with denominator 3, 14 over 3, 15 over 3, etc. And now we will need to look at the so-called characteristic exponents. which are like this. We are looking at the exponents, and we look at the first non-integer exponent. So here the first appears immediately, 7/2. The next one is integer. We do not look at it. And then we try to write the exponents with the denominator 2. And the first time it is not possible, we say we get a second characteristic exponent. Here it's 17/4. And now the common denominator is 4. So let's continue. Can we write this with denominator 4? No. So we have to add it to our sequence of characteristic exponents. And here the common denominator at this point is 12, 3 times 4. Starting from here, everything can be written with denominator 12. So we stop. We have the characteristic exponents. So sometimes they are called Puiseux exponents, but in fact Puiseux never introduced them. So it's just to know, he did many things. Characteristic exponents were introduced a little later, I think more or less by Smith and Halphen, but there is a historical investigation which has to be done there to know exactly for which problem and in which way. And for instance, Halphen introduced characteristic exponents in a little different way. But that's why I don't put a name here. I simply call them characteristic. And now let's see what is an Eggerswald tree. We imagine that we have a germ in fixed coordinates described by 3 polynomials in Y, which are the minimal polynomials of the following Newton-Puiseux series. First is simply x2. Second, x to the power 5/2 plus x to 8/3. In red, I represented the characteristic exponents each time. And the last one that we just saw. So to get the minimal polynomial, each time we have to introduce the conjugate roots. The conjugate roots here are very easy to obtain by an action of the roots of unity. The exponents are the same, simply the coefficients are changed by multiplications by roots of unity. And then what we do is the following. We imagine here that when you read the series, it's like you unscroll, in fact, a cylinder, and you begin to see a text, unscrolling it like in antiquity. And this unscrolling process is done in time. So each time you draw here a segment representing time, and while you discover the text, meaning that you discover the new terms, here you are climbing on this segment. And you have precise moments here which represent the characteristic exponents. And you do this for each series, and then you will see that on your cylinders you have initial parts which coincide, and you glue the coinciding parts. And for instance, when you go to C2 and to C3, you see that up to 5/2 they coincide. Why? Because before 5/2 both series are 0. So their initial truncations there coincide. So this represents the longest part of coincidence of the series. And here one has to pay attention, because it's possible, this does not occur in this example, but it may occur in general, that by replacing a Newton-Puiseux series with a conjugate one, you will get a longer segment of coincidence. So you have to pay attention to the conjugates. But in any case, you get like this a tree which is rooted. Again, it is endowed with a function towards 0, infinity. These numbers being seen simply as evaluations at special points. And here on the leaves, it takes value infinity. And the leaves represent the corresponding branches. So on its structure, you read immediately that you have a curve with 3 branches. And the initial root here represents, in fact, the curve L, which is a y-axis. Why the y-axis? Because at the moment when you decided to express y as a function of x, it meant that you decided to project in this way, meaning parallel to the curve defined by x. And that we said that it is a L curve. So you see, this is important. Here it's not something which depends on a cross, but only on one smooth curve. So here, I said that we have a function with values in 0, infinity. And it seems that we have to put also some special points on it. But in fact, not. Because we have a second function. The second function is exactly the common denominator I told you before. So look, here, before reaching 5/2, the denominator is 1. And if you are following C3, you see that in fact the denominator 2 appears not at 5/2, but at 7/2. So here denominator 1 continues till 7/2. And here we represent between 7/2 and 17/4, the common denominator is 2. So here you see, you can use common denominator 2 for these terms. And only here you have to jump to 4. Till 14/3. And here the common denominator jumps to 12. But if here we follow this geodesic, at 5/2, this exponent appears. So here we have to put as common denominator 2. So there is a second function on the tree, which, unlike the first one, takes only discrete values, positive natural numbers, and it also increases on the tree. But it increases by divisibility. So you see, each time it increases, you get something which is divisible by the previous one. 12 is divisible by 4, 4 by 2, 2 by 1, 6 by 2, etc. So this is a sign that these trees with which we play are to be thought with interesting functions defined on them, with values in posets. And I think that for the moment we see only an initial part of it. And we have to put in our minds that we need here decorations in arbitrary posets. Here you see that you have two different posets. One, real numbers ordered naturally. Second, natural numbers ordered by divisibility. Okay, so I think that I said everything I wanted about this picture. Are there questions about it? So let's pass again to historical figures. Sorry?
So you have taken, T1 equals 0 and at s squared 3, you have the same 3.
So can you repeat?
You take the first series, C, and for the second one you have x to the square.
Yes. If you do this, yes, the tree will be the same. Yeah. And also, yeah, I forgot to say something. Please note here that in this direction, the common denominator is 1 and here is 2. This is a way you know that 5/2 appears as characteristic exponent for C2, but not for C3. Here it does not provoke a jump. And also the numbers here, now you do not have to encode it as special points. They are exactly the discontinuity points of this common denominator function, which we will call the index function. And in the sequel, I will use the two names, as here we have exponents of series. We have the first function, which is the exponent function, which is represented here, and in blue we will have the values of the index function. Why? Because these numbers can also be interpreted as indices of subgroups of abelian groups. So that's the reason of the name. So when Eggers introduced this in his thesis in 1983, Polarinvarianten und die Topologie von Kurvensingularitäten, thesis written under the supervision of Briscorn, he represented it a little differently. So you see it here. First, he looked in generic coordinates, so that's why he always started here from rational numbers which are bigger than 1, and he did not start from 0. And in fact, to start from 0 is part of the process which led us, using our experience, to see that if we want to get trees which are perfectly isomorphic, we have to care about the axis of coordinates. not representing the first part here means that no, I only care about C. I want to remove the axis of coordinates. Our moral is that if you want to remove them at the end, at the complete end. Because if you remove them initially, all the isomorphisms of trees I will show you are not true. So sometimes the hypotheses are to be chosen such that you get simple statements and put what destroys the simplicity at the end. So this is part of the structure of our text and our explanation. So why Eggers' wall? Because later Wall used the same tree, but he understood that the conventions of Eggers, you see that here you have different segments, some of them are dashed and some others not. So he had conventions like this in order to encode precisely this phenomenon, that at a bifurcation point, an exponent can be characteristic for one and not for the other. And it was CTC Wall in this paper of 2003 who understood that for the computations it is very convenient to introduce the second function, which we call the index function. And that does not allows us not to decorate edges in different matters. So you have now a tree and two functions defined on it. A little later, before, in 1977, Kuo and Lu introduced a different tree, which you see here. So what are the differences? First, that instead of having a point from which pop up new segments, they drew horizontal segments here. Those horizontal segments have an advantage that they allow you to think about the variation of the coefficient at the term where you have bifurcation. But if you contract them, you have trees like I just showed you. But there is a second difference, that for each branch, they have one leaf per root. So you have more leaves. And how to get from this Eggers' wall tree? Remembering that you have the Galois group, which acts on the roots, which is simply cyclic there. And if you quotient this tree by the Galois action, you get the Eggers' wall tree. So the relation between Kuo, Lu, and Eggers' wall is that you have a covering, which is a Galois cover of trees. And in fact, the numbers which appear here, which were introduced by a CTC wall, are simply that if above it you imagine the Kuo, Lu tree, above this segment here, you will have 2 segments. And above this one, you will have 12 ones. So those represent degrees above those segments. So you see, the theory of covers of trees is a little more sophisticated. The degrees change. You do not have a generic degree, like for covers of Riemann surfaces. But this was my only mention today of the Kuo, Lu tree. Now we will follow the Eggers' wall tree, because it is this tree which will get identified with the dual graphs and the Fan tree and something more. So now this page is an analog of the page, corresponding page for Newton polygons. We ask what is the geometrical meaning of the Eggers' wall tree, and it turns out that it depends only on the analyzed curve and on the curve defined by x equals 0. So not at all about the curve defined by y equals 0. So now in your mind, if you see somewhere a smooth germ and any other germ, you have to know that canonically associated we have such a tree with the 2 functions. So in particular, if you have a cross with the order first curve, second one, and a germ, you have also an associated Eggers' wall tree there. So you can ask then, well, it means that when I have the final lotus, I can ask how to get from it the corresponding Eggers' wall tree. And this is what I want to explain you. So I want to explain you how to compute a tree and 2 functions on it, the index function and exponent function. And note that now we denote them only through the geometrical elements which determine them. They depend only on L. And they are defined on the Eggers' wall tree of C relative to L. This has a meaning once we understood this fact. So this is a question, how to pass from the Fan tree to the Eggerswald tree. And I will also show you how to pass from the lotus to the Eggerswald tree. If you remember, I showed you before how to pass from the Fan tree to the lotus. So now we have Fan tree, lotus. We want Eggerswald tree. So I will show you two direct paths from Fan tree to Eggerswald tree and from lotus to Eggerswald tree. From the viewpoint of the Fan tree, one has to do integration on it. So what does it happen? The underlying tree does not change. The Eggerswald tree for this extended curve, and here you see I put it in red. It's the first time I introduce this notation. This toroidal pseudo-resolution process led to an operation of completion of C. I had put a C hat, and pi denotes the composed morphism, in which we added the new curves. So you see, in fact, here, the curves which, the curve C has branches represented here in green. But the new branches which are added are here in yellow, in blue, sorry. So you see that the completion adds to the green ones, the blue ones. And you see that this has also a dramatic effect on the tree. If you remove these blue parts, the topology of the tree changes. And this is a change which makes that the identifications are not possible if you do this. So you need to do this to get a perfect identification. So simply I say from these numbers you pass to new numbers here by an integration. So what is the integration? I will show you how to compute here 11 over 15 starting from 2 over 3. So you have to go from the root to 2 over 3 and to do the following. First here you compute a measure of the discontinuity. I said that here the slope function goes from 3 over 5 to 0. So here you look at the denominator 5. So this 5, you put it as a decoration on this trunk. This is a 5 appearing here. For the same reason, 5 decorates also this. Here you see that you have another jump, a new denominator 3. So you have to multiply 5 by 3. That's why you get 15 here. So this 5 is multiplied by 3 when you get here, so you get 15 till you get here. So the first thing you compute are these numbers, which appear as products of denominators of the rational numbers which are here. These are the rational numbers which are the slopes of the dual fans of the Newton polygons. And now you can integrate. We will integrate, in fact, the slope function from here to here, but, we will integrate with respect to the differential of the slope function. And what we will integrate is the inverse of this. So till here it is 1, so we integrate 1 from 0 to 3 over 5, we get 3 over 5. That's why here you see 3 over 5. And that's why here along this segment the numbers do not change, because they are decorated by 1. But now from here to here you have to integrate 1 over 5 on this segment, which goes from 0 to 2 over 3. So concretely you have to multiply 1 over 5 by 2 over 3. This is 2 over 15. And please imagine now that you add 3 over 15 and 2 over 15. Common denominator 15. Here we have to multiply by 3. So we have 9 over 15 plus 2 over 15. We get 11 over 15. So this is a process. And in this way you understand also all the numbers here. You know from what they are built. From parts of the fan tree. And the fan tree, now you can unfold it into the lotus, and you can then interpret them also in terms of the lotus. And you know each one of them, it measures which part of the lotus. So here are the formula which I just explained you, how you compute the index function as a product of denominators, and then how you get the exponent function by integrating the inverse of the index function with respect to the differential of the slope function. These are the formula which show how you do integration on the tree. So these are the first formula of integration, which allow you to pass from the fan tree to the Eggerswald tree. If you want to go in the opposite direction, for instance, if you started with Newton-Puiseux series and you drew the corresponding Eggerswald tree, you first have to add curves till you know that you have enough of them to have the new axis of coordinates, and then you have to decompose into trunks. That is not canonical. You have several choices of trunks, but once you do that decomposition into trunks, you can invert this. You know that the opposite of integration is differentiation. You differentiate, you integrate in the opposite way, and you can pass from Eggerswald tree to fan tree and to a lattice. This is the way how you pass from Newton-Puiseux series to the minimal resolution. So now I told you that I will explain also how to pass from the lattice to the Eggerswald tree directly. This is useful if you want to go in the direction I have a dual graph. So first the dual graph, I look how it is built by blow-ups. That process of blow-ups I represented by the lattice. And now, from the lattice, I want to write Newton-Puiseux series. So first I will compute an Eggerswald tree. So what do? I come back to the Farey additions. But just, you remember, Farey addition started here from 0 over 1 and 1 over 0. Here we change only one thing. We put 1 over 1 here and 1 over 0. And then we continue. By adding these two, we get 2 over 1. These two, 3 over 1. These two, 4 over 1. These two, 7 over 2. In this way, we reach here to 8 over 5. And then each time you add a new curve in a new cross, you put again 1 over 0, the one which was here. And you continue. 8 over 5 and 1 over 0 gives 9 over 5, etc., etc. And in this way, you reach at these numbers. And now, topologically, the Eggerswald tree is the lateral boundary of the lattice. So just I drew those straight. So you see this segment is this one. Here, this one arrives here. Here I have two arrows. They are transformed into these two segments. I continue here, and then the final one. So this is simply drawing differently in the plane the lateral boundary of the lattice. And now these final numbers, I just have to subtract 1 from them. So for instance, here 8 over 5 minus 1 is a 3 over 5. It is a 3 over 5 here. The 26 over 15 minus 1 is 11 over 15. The 11 over 15 here. And that's how you get the exponents. And the integers which are here, well, just look. We want to know what happens, for instance, here. Why do we have 15? This point here appears from here. Well, here you see the denominator 15. So the index is simply written on the denominators of the Farey computation. So this is extremely rapid to do in examples. So for me now it's the most rapid way if I say, well, I want to get this process of resolution and now I want to write Newton-Puiseux series corresponding to it. I do this Farey addition which is extremely rapid, and that's why students would like to add fractions in this way. I draw this, and now from here you have all the instructions to write the Newton-Puiseux series immediately. You have, of course, many choices because they are moduli, but if you want only an example with the correct topology, you get it immediately. So the formula I just showed you are like this. Here, I did not interpret what were these numbers with which we played, green ones and red ones. On this new page, I give the interpretation. So first I told you that the exponent is a fraction minus 1, but what are the numerator and the denominator? Well, the numerator is simply the log discrepancy of the corresponding exceptional divisor. We learned that the boundary of the lattice represents the dual graph of the exceptional divisor. So each vertex represents some component. You can lift holomorphic volume form on the starting surface to that surface. There it vanishes, and simply you add 1. From this viewpoint, combinatorially, it's completely understandable why to add 1. Because if you do not add 1, you do not have that Faraday rule, that the new log discrepancy is computed simply by doing an addition. And what is the second number? It's simply that you look at the order of vanishing of x, which defines the preferred curve, L, which is here, the starting point. Everything starts from this point, which is the first curve in the cross. So if you look at the order of vanishing on this, on the component, this is a denominator. And it turns out that on the lotus, those orders of vanishing are also additive. So simply, they have different initial values, because one of them starts here from 1 and 1, and x, well, x vanishes at order 1 on this curve, but at order 0 on the other curve. So that's why you have these initial values. But then you have additivity on the lotus. And for many others orders of vanishing, you can compute them very easily on the lotus because you have always a form of additivity, which makes anything very easy to compute once you have this drawing on your page. So this we did not explain in the text in the handbook, but in a previous text, the valuative tree is the projective limit of Eggerswald trees. It is a point where we studied in general this formula, and we compared with analogous formula from the book of Favre and Johnson, the valuative tree. This was a work in which we gave different construction of the valuative tree based not on blow-ups but on Newton-Puiseux series. And we explained that in fact if you add more and more branches to infinity, the final Eggerswald tree you get is the valuative tree of the initial Germov surface. Let me explain you a particular case. If you start from one branch, then the corresponding lotus has the following shape. We simply glue in order elementary lotuses corresponding to one rational fraction. So each one of them has an internal structure, as I explained you. A triangle, a zigzag, and then each triangle here is subdivided into some numbers. I call them P1, Q1, etc., P2, Q2, etc. So I showed you that the rational number corresponding to each one is a continued fraction obtained from P1, Q1, etc. So let's call it dg over ng. So you see that each one of these triangles gives you a pair of integers. What is the meaning of this pair of integers? They are very similar to what are called the Puiseux pairs, which Puiseux did not introduce, but it is a common denomination. And here it is important, because in general in these computations, there are two sequences of pairs which appear, and they need two names. And so people, I think, split Newton-Puiseux into Newton and Puiseux. So these are, in fact, the Newton pairs. How are they related with the Puiseux pairs? Is simply that a series with this topology is the following one. You write only the sum of characteristic monomials. The first one, you write it as m1 over n1, with m1 coprime to n1. The second, m2 over n1, n2. And here the second pair is m2, n2, which is unique if you say that they are coprime. And you continue like this. But then this you can rewrite it in a multiplicative way by factoring through the smallest monomial. This will give x to the power d1 over n1. This is the first Newton pair. It will be equal to m1 over n1. And then you say is this times 1 plus, and then you start again factoring in the same way. And then you write in the same way as before, d2 over n1, n2, etc. And you get a second sequence of pairs, d1 and 1, d2 and 2, etc. These are the Newton pairs. And from here, it's very easy to write the formula which pass from one to the other. It is not this my object. It is the object to explain you what is this, that the quotients which give you the internal structures of these lotuses here are those of the Newton pairs. so not of the Puiseux pairs. So you see here, you have a geometrization. You do not need more numerical decorations, which encode completely the characteristic exponents and also the Newton-Puiseux pairs. Because of the additive process, you understand also that each Newton-Puiseux pair is obtained by an integration in which you increase like this. By the way, in this case, the curves which you add here have the topology of the approximate roots of the initial function. And those with that topology have other names like approximate semi-roots, for instance. And therefore, those which we use for building the general lotus are generalizations of approximate semi-roots to cases which are not irreducible. And the moral is those semi-roots are always important if we want to understand the correspondences between the different numbers and different computations. So finally, the last tree, which has the same structure, is a splice diagram of the link. Here we pass to the field of coefficients, the complex ones, and we assume that our germs are not formal but convergent, which allows to do the Milnor type construction, or say Brauner, Keller, Zariski type construction of cutting with a small sphere and getting a link. Well, it turns out that that link also can be encoded by a tree, by a construction initiated by Ziebenmann and Eisenbud-Neumann in the 80s, which is called a splice diagram. I won't recall it here because that goes in another direction, but just it is a tree with other kinds of decorations. And the question is, what is it? Well, topologically, it is the same as before. So once you constructed the fan tree, or the dual graph, or the Eggerswald tree, you have also the splice diagram. And again, what changes is the way to decorate it. So how to compute the decorations? Well, here one needs to understand the intersection numbers of the branches from the Eggerswald tree. Because, in fact, the splice diagram is extremely adapted to understanding things about intersection numbers. Because intersection numbers of branches can be computed on the splice diagrams by very funny rules of multiplications along geodesics. So first, here comes a second integration. We are on the Eggerswald tree, which is the same as before, but meaning that we have on it the two functions, exponent function and index function. Now we need to compute a new function on it. It looks like the first integral, which allowed us to compute the exponent. Recall that the exponent was the integral of the inverse of the index, but with respect to the differential of the slope. So now here we compute with the differential of the exponent, which means that in terms of the slope, this is the integral of the inverse of the square of the index. So if sometimes in your computations you see squares appearing in the denominator, I bet that the numbers with respect to which you compute are in fact slopes of rays orthogonal to edges of Newton polygons. So you see that from this viewpoint you begin to interpret, to know, well, in terms of which tree I could understand my computations in the easiest way. So once you define this contact complexity, you have a formula which was, of course, not expressed in this way in the 19th century, saying that you can compute the intersection number of two branches starting from the value of this contact complexity. So here you see this wedge. I will show you what this formula means in an example. The same example. Assume that you want first to compute the contact complexity. So you pass from the Eggerswald tree to the same tree. The index function does not change, but again, we put new numbers here. And we have to know, for instance, what number to put here. We do the same process as before. We integrate the inverse of this. So Here the integration gives 3 over 5 minus 0. It is this term. And then we have to integrate here. 1 over 5 times 11 over 5 minus 3 over 5. When you do this computation, you arrive at 47 over 75. It is a number which is here. And in this way, you compute the contact complexities at all the points. And you understand how they are related with the exponents of the Newton-Puiseux series. And now you can ask, what is the intersection number of these two branches? You remember then that this is a rooted tree at L. You look at the union of geodesics joining the 2 points here to L, and you see that the geodesics bifurcate here. This is A wedge B with respect to L. It's simply that the rooted tree can be seen as a poset in which every 2 elements have a greatest lower bound, and this is what we denote in this way. And topologically, it is this bifurcation point. And there, we compute the contact complexity. So we saw that it is 47 over 75. This is a quotient of the intersection number which interests us, and the intersection numbers of A and B with L, which is the initial branch here. But these 2 numbers are exactly the final indices here when you reach this, 15 and 20. So the moral is how you compute the intersection number of these 2 by multiplying 15, 20, and the contact complexity here, 47 over 75. And in our case, we get 188. So this is a general rule. Now, how do we pass to the splice diagram? This is again something which we explained in our paper, the variative tree, the projective limit of Eggerswald trees. In general, if you have any Eggerswald tree, so not necessarily one associated to this Newton process, you make elementary moves which are like this. In the Eggers, so first, the numbers with which we work are the indices of the edges and the contact complexities, not the exponents. The contact complexities decorate the vertices. In the splice diagrams, vertices have no more decoration, only germs of edges. So we have to change all of these in decorations of the edges here. So what is the rule? If you climb in the Eggerswald tree and here the indices do not change, then all of them above are 1, and below you have d squared times s. If you have this second thing that they change, but also in one direction, they do not change, you pass from d to d, then you have this other rule. Here you have a change, and I told that the indices change by divisibility, so d prime over d, which appears here, is an integer. And again, you have d prime times s. And the last step when the topology changes is this one. If at some vertex you do not have an outgoing edge where the index remains constant, there you have to add a new segment to pass to the splice diagram. But in our case, in which we put all the crosses, this never happens. That's why we do not have a change of topology, and that's why the splice diagram here is the same as the trees we saw before. So it's again the boundary of the lotus. So if you do the game here I showed before, you get all these decorations. Okay, it's easy. I don't have to explain you more here because it's very easy to do on examples. And now, how do you use the splice diagram to compute intersection numbers? I want to do the same, to compute the intersection number of A and B. Then I take the geodesic between them. So you see, I do not have to look now at the geodesic to L. This part does not interest me anymore. I look at this, and I look at the edges which get out of it. And I look at their decorations. I have 47 here and 4 here. I multiply them. I get, again, 188. So depending on your context, depending on your taste, you can compute intersection numbers either from the splice diagram or from the Eggerswald tree. And I showed you how to transform one into the other. of course, that these operations here can be inverted. And you can also transform splice diagrams into Eggerswald trees decorated with contact complexities. And from contact complexities, you can get the exponents by the same integral formula. You differentiate them, and then you integrate in the opposite way. And in this way, you can travel from any interpretation to any interpretation on the same tree. Everything is analysis on a fixed tree, which is the lateral boundary of the lotus. So what is an overview of what I told you till now is that we have this Newton resolution process in which we see some fans. The fans are transformed into trunks. Either directly or through the trunks, we have associated Newton lotuses. And then the trunks are glued by identifying points with the same labels into a fan tree, which gets interpreted also as an Eggerswald tree and as a dual graph and as a splice diagram. And this embeds as a lateral boundary of the lotus obtained by gluing this. And the gluing is the same identification of points with the same labels. In order to get these identifications, which means that all these trees are the same, here between absolute values I represent the underlying space without decorations. It's very important to complete the initial plane curve singularity using all the crosses this is very bad expressed. I am very sorry, it was written too rapidly. Used. Wow. Counterexample of how to write mathematics. And now, for the, say, 3 last minutes, rapidly, perspectives. All these objects have canonical valuative interpretations. How? First, that book by Favre and Johnson, The Valuative Tree, in which they explain that the valuative tree is a projective limit of dual graphs. Of what? Of all sequences of blowups. Then the work I just mentioned, done also with Evelia and Pedro, the valuative tree is a projective limit of the Eggerswald trees. Then, in a work done also by the 3 of us and in collaboration with Matteo Ruggiero, second part of a work we did before alone, intersection number of branches lead to ultrametrics on arbitrary normal surface singularities. This answers partially the question, and if the starting germ is not smooth, what can be done? Well, one can build trees by first building ultrametrics on spaces of branches. When the singularity has resolutions whose dual graph are trees, that is very easy. If they are not trees, it is more subtle. Finally, lotuses are two-dimensional objects. Well, lotuses also embed in the valuative space. The valuative space is in fact the space of all semi-valuations of C2, such that the valuative tree of Favre and Johnson is a quotient of it. So before making the quotient, we have enough dimension to embed the lotus inside it. And there are also tropical interpretations in a recent work with Ana Belén de Felipe and Hussein Murtada. Pedro González Pérez proved that one can resolve any plane curve singularity by one toric morphism after re-embedding it in a bigger dimensional space. In order to embed it, one has to add new functions. Which new functions? Exactly those defining the crosses appearing here. So also those crosses which allow to identify all those trees allow you to resolve anything in one toric step, and they give you the instruction to do the embedding to reach this. And there also they interpreted the local tropicalization of the embedded surface in terms of the tree. Simply, it is a cone on the same tree. And this we generalized in a paper with Maria Angelica Cueto and Dimitri Stepanov for the more general class of Neumann and Wall splice type singularities. Are there other applications of lattices accepted as a unification of all these combinatorial objects? Yes, and I think a lot remains to be done in this direction. They allow, for instance, to study delta constant deformations of plane curve singularities. A prototype of this, which I learned due to Wolfgang Ebeling, is a work done under the supervision of Briscorn again by Schulze-Röbecke, Algorithmen zur Auflösung und Deformation von Singularitäten ebenen Kurven. And in fact, he looked only at branches, and he applied a campo deformation algorithm, and he explained that he can obtain special deformations in which you are able to describe completely using the characteristic exponents. And the drawings which he made, you see that you have here parts of the lattice of the branch. And this was generalized by my PhD student, Roberto Castellini, who did this for an arbitrary number of branches. When I gave him this PhD project, I did not know about Schulze-Röbecke's work. And in fact, when I explained part of this work to Wolfgang, he told me, an old friend did this in the 70s. And Roberto was not at all happy at that moment. But then I explained him that this is in fact very good because he had proved a more general result in a setting where there was no conjecture. Well, for a branch it's like this, and when there are many branches, what to do? And what he discovered is that you have an algorithm of computation of numbers on a lattice which allow you to draw such curves in the plane in any way. And in fact, Schulze-Röbecke's result shows that in fact it is unavoidable. So what had discovered Castellini is a generalization of something done more than 30 years before in a different context. So in this sense, I think that for these problems of delta constant deformations, lattices are unavoidable. Another part of his thesis is that if he applies a campo deformations only partially, he does a lot of delta constant deformations in which appear singularities. With which topology? Well, the corresponding lattices are sublattices of this. So typically you see a way, what is allowed by a lattice, that you can look for a given lattice at all the sublattices. If you try to express this in terms of any other tree with the corresponding decorations, it's very complicated. So I think that some questions about singularities have answers which depend on taking sublattices of given lattices. And precisely this direction of research, I think, has a lot of questions. But it's not clear for us exactly what are the initial ones which we should attack. So here I think that there is a lot to be done by young people. Enrique's diagram. Well, my time is over. I just pass rapidly to them. We have to remove some parts of the lattices, which are the parts which do not depend on the added curves. And then the Enrique's diagrams can be seen like this. And in particular, this is the first drawing I did of this in the paper in which I introduced initially lattices in 2011, and I called such objects kites. So the kites from this, our viewpoint, are lattices I presented you, which are cut in order to keep only the part which depends on C, and then you have some ropes which are added there. And the curved edges in Enrique's diagram are the free ropes which can go in the wind in the sky. The other ones are glued to the petals. Well, a true lattice is this. Thank you very much for your attention.
Thank you, Patrick, for this interesting two talks. Any question, remark? Okay.
Thanks. Thank you for the talk. It was really nice. So I wanted to ask, because you mentioned like several things you can compute from the Lotus, and one of them was the log discrepancy. And I wanted to ask if you can also compute the order of vanishing of each branch
Yeah.
at the divisors of the resolution from the Lotus.
It's again an additivity formula, but we have to complicate it a little more by first computing from the end to the base the multiplicities of the strict transforms of the base. So it's a double movement. You go from the arrow of the branch, you go down, and now you knowing those things, you can climb again. So it's, you see, the advantage is now you do not have to say only I do this computation, but you can follow the path in the Lotus. So all the computations of orders like this can be followed very nicely in the Lotus, and then in concrete examples you do them very rapidly. So the advantage is that you can do them by hand. So that's very nice. Yeah.
Thank you.
Alejandro.
Do you have an idea that this can be done for quasi-ordinary singularities?
I think less than you. I heard that you are thinking about this for quasi-ordinary. I did not think about it, so I'm sure that now you have much better ideas than I.
Any other question?
Can you somehow read the topology of the Miller fiber in the Lotus?
So, yes, but we did not describe this. And I think this is more or less doable thinking in terms of splice diagrams. Yeah. But it's something which we did not describe.
Kike, please.
Yeah. So I am not to ask all the questions I have in mind because you raised a lot of them. But I think you said that for any normal, a curve in a normal surface singularity, you could also construct a Lotus or...
Not a Lotus. In fact, Lotuses are really something which unify all these various viewpoints, which are typical of smooth germs of surfaces. Yeah. Mm-hmm. If it is not smooth, it's normal that something is lost. Yeah. But what we still have is a tree. Mm-hmm. Which we construct using looking at intersection numbers of branching on them in the sense of Mumford. Yeah. That is a rational valued intersection numbers. Yeah.
But then for cyclic quasi-singularities, maybe you may have, because in that case you have also this, you can add, you have also coordinates in some sense.
The thing is that each time you start from a resolution of the surface, because it is smooth, from that point on, if you keep resolving, for instance, if you need to eliminate base points of linear systems, things like this, there you can begin to think in terms of Lotuses. Yeah. Mm-hmm. There. But before, what you will have are a priori only the dual graphs, which you can interpret in terms of intersection numbers, using our paper, in ultrametric terms.
And then just last, I think that maybe, so in some sense, if you fix this L, it can be interpreted like, for example, in the case of irreducible germ, you are looking at the intersection number with a smooth branch. Yeah. And so, for example, in that case, the Newton-Puiseux expansion gives you a conjugacy class of a braid. It's more or less. I think that maybe it can be also constructed from your Lotus.
Yeah, one has to think, but.
More questions? No? If not, we thank Patrick again for these very interesting and nice mini courses. Now we have a break of a few minutes, and we start again at 5 to 11. Okay?
Carramiñana from Barcelona Tech, and she will talk on the title you see there, the minimal Turina number of equisingularity class of plane curve singularities. Maria, please.
Thank you, Antonio. So this is a joint work with Patricio Almirón, Guillem Blanco, and Alejandro Melle. First of all, I would like to thank the organizers and the scientific committee to invite me to give me this talk in the honor of so accomplished mathematicians as Enrique Artal and Alejandro Melle. Well, I want to start saying that from the very beginning of my scientific career, I had the pleasure to know Alex and Kike. So I found in my notebooks these drawings. So the one in 1994 from Alejandro and the one from 1997 from Kike. So perhaps some of you know that at the beginning of when I start as a student, as a PhD student, when I started attending to conferences, my notes were scattered by drawings and caricatures of mathematicians, meaning that I share with them moments and memories. So when I found these caricatures from both of you, so I remember the good moments that we spent together, and I will want to thank you for them, because from the very beginning you were very friendly and supportive, even for young people who are in the early career. And now let's focus on the problem. So here we have, we will start with plane curves, or we will focus on plane curves. So plane curves that are irreducible on branches, so defined by some equation. And then the problem here is to understanding to which extent an analytical invariant, so when you have dealing with objects, so in the case of curves, you have two main equivalences. One is the analytic equivalence, which means that you can transform the embedding in C2 of the curve to one another, preserving the curve. And another one is a topological equivalent, which is the same, but you only are restricted to use homeomorphisms. So since one is strong of the other, so analytic is stronger than the other, you may think at this type of problem. So when you have an analytical invariant, to which extent the topology of the curve determines it. So this is a framework of our study. And here there is also a notion that you may know, which is called equisingularity. So equisingularity means that two curves behave the same way when intersecting two other curves. So in this sense, equisingularity, you may say that it is equivalent to the topological equivalence that I previously said, okay? So it's an old result by Brauner, Bureau, and Zariski. And here we will tackle about two main invariants. The one is a topological invariant, which is the Milnor number, which is the dimension of the Milnor algebra, which is the quotient of the full ring by the gradient ideal. And the other is an analytical invariant, which is the Turina number, which is the dimension of the quotient of the full ring by the Jacobian ideal. You see we have added in the discriminantal ideal the equation of the curve. And now I make a complete picture of all the invariants we will be dealing with. So we start with a plane branch, and then we take the Jacobian ideal, as I told you. And there are some topological invariants which are called complete. Complete means that from these topological invariants you can recover the topological class. So some known complete topological invariants, very well known, are the semigroup of values, who has already appeared here. So it's just taking the, you intersect your branch with any element of the ring, and this is a semigroup. And the other one is the sequence of positive multiplicities of any resolution of the branch. So the multiplicity is the minimal degree of your equation, and then you take this at any strict transform of the curve at any blowing up of the resolution. Resolution meaning that you get a smooth curve at the end. So these two invariants are complete, so they are very interesting topological invariants since they encode all the information of the topological class. And then you have another invariant, so this will be the multiplicity at the origin, which we will denote it by n here in this talk. I want to fix this notation. And also the Milnor number, which also can be read in terms, so you have the Milnor number, you see this, that before as a dimension of the Milnor algebra, but you also can see it in terms of the semigroup as twice the number of gaps of the semigroup. And you also have an expression of it in terms of the sequence of multiplicity. So I will focus in these two invariants, complete topological invariants, and I'm describing this Milnor number in terms of both of them, okay? And then if we switch to analytical invariants, here the stars, so the counterparts of the semigroup will be the Jacobian values. So you take all the elements of the Jacobian ideal and intersect with your branch, and you shift it in some way that you have a gamma semi-module. So you only shift it in such a way that it's you have much more structure. Sorry. And then the Turina number can also be expressed as the Milnor number was in terms of the gaps of the semigroup. You also may express the Turina number in terms of the gaps of these Jacobian values here in this formula with appearing the Milnor number and the multiplicity at the origin. And of course, refreshing some ideas to some of you perhaps, so the most younger ones. So there are also complete analytical invariants. I will not be talking about them because I will focus on the Turina number here, but I recall that the isomorphism class of the local ring algebra is a complete analytical invariant, of course, and also by a result of Mather and Yao, you also have the Turina algebra, C algebra as a C algebra isomorphism is also an analytical invariant. So in this framework, we want to, so I'm just copying the things that are interesting me from the previous slide here. I will denote by gamma the semigroup when it is clear, because we will fix a topological class for all the branches, so I will fix the semigroup, so gamma will be this semigroup. And then it makes sense to consider the minimal Turina number among all the curves in this semigroup, okay? And this tau mean will be in which we will focus because it happens to be also a topological invariant. So it comes from an analytical invariant, the tau, and inside the class of all the curves which are in this semigroup, we have the same topological type. We take the analytical invariant of one which achieves the minimum there, okay? And now we want to know in which way do the topological invariants determine these analytical invariants. So, of course, we have, as I've told you, that the values of the Jacobian is a gamma semi-module, and we also have, since the definition that any Turina number is strictly bigger than this minimum Turina number. And since this is a topological invariant, here our goal was to give an explicit expression of this topological invariant in terms of a complete topological invariant. So we wanted to get a formula of this tau mean as we got this formula for the Milnor number, okay? So recall the formula of the Milnor number was expressed in terms, in terms of the sequence of multiplicities. Then we wanted here to express the minimal Turina number in terms also of the sequence of multiplicities. We wanted a closed formula. So some history about this problem. So this tau mean, we knew how to compute it by Peraire's algorithm in '97, and her approach was the following. So he was able to compute from the semigroup, so from the topological type, the values of generic elements, of the values of the Jacobian for a generic element of a generic branch within a topological class. And this was an algorithm, and since then the tau is upper semi-continuous. This generic curve, so she was able to prove that choosing generic coefficients in the Puiseux series, she was able to give these generators, and then with applying the result that the tau is upper semi-continuous, in fact, this generic element gave the tau mean, which was what she was looking for. And she applied this formula so we have this tau mean for the generic one, so we can apply the formula which relates the Milnor number and the gaps of the semigroup we also had there. So here, then, the problem is to be able, or in some sense, to compute this, which we were not able. So there was an algorithm, but we didn't know how to make an expression there. And also, this is the idea. This framework is also the idea of the classification by Jefez and Hernandez, and their algorithm in 2011. In fact, at least from the discrete part of their algorithm, they also take this. So they are working with Kähler differentials, but Kähler differentials is equivalent to the Jacobian ideal. And then with Gröbner basis, they compute also from the semigroup for each curve, because the algorithm works with you start with a fixed branch, and then from a branch, you compute the values of the Jacobian, and then from the values of the Jacobian, you get the tau of this branch. So the difference is that the algorithm work with concrete curves, and this was for the generic one, but it is also the same scheme. And now our goal was to give this closed formula, and we also were motivated for the Dymka-Groyal question that they arose, saying that can we bound the quotient between the Milnor number and the Turina number by 4/3 for any plane branch? And if we were able to give a closed formula for tau mean, then we will get, if we prove this inequality for tau mean, then we will have a positive answer to Dymka and Groyal question. So I start this presentation by the end. So I start by presenting the result, and then I will explain how we got it. So our formula looks like this. So this formula was also discovered at the same time by Gensmer and Hernandez, and they arrived to the same formula by by different techniques. I will explain you which is the difference, because some key ingredient is the same in both works and some other it's not. So I will explain the difference. But so we have this formula. It appears that n is the multiplicity at the origin. Then you have the sequence of multiplicities at all the blowing ups, and you have this sigma, which is a function depending that that modifies your input in some way, as stated here. So this is our formula, and I'm going to derive from this formula the answer to Dean-Campbell-Royal's questions from here. But I wanted at the beginning to understand a little bit, because here you understand all, but here there appears the name free and satellite. So okay, there are some points in the resolution of a singularity which are called free, and others are called satellite. I will explain this notion here. So, for instance, when you have the embedded resolution of the simple cusp, you have several blowing ups in the process, and at each blowing up, so I have it easy because Patrick has explained a lot about this. So I'm focusing here on this. You can think of a blowing up of a change of variables. In fact, you can think in this chart, assuming that you have not vertical tangents, so you can stay at this chart. So you have an isomorphism of a smooth surface to your surface outside the origin, and then the origin there, the pre-image is a full divisor, and now each blowing up that you see this point, it arises a new divisor, and then if we blow up the crossing, we have a new divisor, and so on. And we can choose a point inside a divisor, either inside or at some crossing, because we always have at this process a normal crossing divisor for the exceptional divisors that are appearing. So the points are free if they are on one divisor when they are chosen to be blown up, and satellite when they are at some crossing. So we have this, and we also have a relation that will appear somehow later, which is called 1.1 infinite linear point. Infinite linear point meaning that it will appear at some blowing up. It's not there, but it will appear, so it is infinite linear. And now we have that some point is proximal to another if when we want to blow this point, it's on the exceptional divisor of the preceding one. So in this way, so it makes, so when blowing up to point proximal to another, so in the sense of Patrick, you are increasing the auto-intersection of the preceding exceptional divisor. And now, so our corollary is that we get a positive answer for branches to the Dean-Campbell-Royal question, because from our formula and the Milnor formula that we had, so we had both expressed with in terms of the multiplicities of the resolution of the singularities. So we had this here with both formulas and using this bound here for the operation sigma. And so we have to finish this, but before finishing this argument here, I wanted to comment that, in fact, so if you are wondering about the general result about any plane curve, not necessarily irreducible, so for a general plane curve, the Dean-Campbell-Royal question was answered positively by Patricio Almirón in his PhD thesis, and he solved the question for any curve. So, but this being said, so we focus on the irreducible case because we want more. We want not only to answer this question, we want it a closed formula for tau mean. Okay, so in the last slide we were up to here, and we wanted to have a bound. So we have here some positive terms and some negative terms, and we wanted to see that these negative terms were not so bad to turn this negative. So, we had this lemma here. We proved this small lemma which says, okay, the multiplicities of the resolution at the satellite points, when you sum it, it's exactly the multiplicity at the origin -1, and that enabled us to make this equality and then the desired bound. So, yeah, that finished the proof of the Dymka-Groyal question, and let's see. And let's focus on what was our approach to give a closed formula for tau mean. So our proof has three key ingredients. So we use Gensmer formula, which was given on a formula by Gensmer given in 2020. So this is the same as, of course, the work by Gensmer and Hernandez. They also rely on his formula. And we relied on some old formulas by CTC Wall and also recovered by Mattei and generalized for foliations. So I include here the work of Mattei because it was the first reference that I looked into it. So, and then well, in fact, we realized that it was already in CTC Wall's papers, the formula. And for us, the way to glue both formulas is by all the theory that I will recall here by Bernard Tessier of moduli space of monomial curves. And this is the left-hand side formula is what we make different from Gensmer and Hernandez. They developed in their paper some theory that they not use this formula, so we knew this formula. We had the things very, very straightforward, as we will see. So, but we had to prove that we could use this formula. This is the point. So let's begin with. So when we have a topological class of a branch, so let's fix a topological class by fixing a complete topological invariant. Let's fix the semigroup. So when you have the semigroup and you have a minimal set of generators, then also making use that the Turing number is the base of a miniversal deformation of the curve. So the approach was this. So let's compute this, or let's make let's make use of formulas about this. And then we wanted to consider deformations, but as we know, when you have one characteristic exponent, you have the quasi-homogeneous curve that is the worst analytical type of curves, and from it you can deform. Here, when you have more exponents, then you have this object, which is Tessier's monomial curve, that enables you to also have this same of result that for one characteristic exponent. Then what you have from the results by Tessier is that then when you have each branch that you are looking for, so each branch with this semigroup is analytically isomorphic to one fiber of the miniversal deformation of the monomial curve. And if we restrict the base to the miniversal constant semigroup deformation, so we will be interested in semigroup constant deformation because we want to remain in the same topological class, then we have this deformation here, and each base has one dimension. So the miniversal deformation is the base of the dimension is mu, and when you restrict to the constant semigroup deformation, your dimension of the base is tau minus. Okay, so this tau minus will be, so the interpretation of this tau minus will be the key, you will see. So Tessier's result says that the miniversal deformation of the monomial curve is a versal deformation of each fiber. And now, with this, so we can take any fiber and then consider, so we are looking for the tau of this curve, so of some generic curve, or some that achieve the minimum. So when we have the minimal deformation of one fiber, and we have some base, which the dimension we know by definition or by equivalent results that this is the tau, the Turing number of the curve. And then if we restrict to the constant semigroup deformation, so we restrict to the same topological type, then we have some dimension of the base, which we'll call it Q of this branch. So by Tessier's result, by base change of these deformations from the monomial curve, we have that the difference between the Milnor number and the tau minus is equal to the difference between these two dimensions here. Now I want to mention that, in fact, all the construction by Tessier, in fact, when you have analytical equivalence of germs, it also induces analytical a relationship in the base of the semigroup constant deformation of the monomial curve, and then this object with the quotient topology, we also can consider the natural projection, and inside here we also, so in the construction by Tessier, you started some planar problem, and you switch to some G+1, depending on the number of characteristic exponents, on something in higher dimension, but you are so you have deformations of the monomial curve that are not interesting to you, in fact, but you are only interested in those deformations that, in fact, come from plane curves. So Tessier proved that, in fact, these fibers all these fibers constitute an analytic open dense connected subset of all the base, and also that, in fact, this projection moduli, the analytical equivalence, in fact, was the moduli space considered by Zariski. And now, so we are considering a generic fiber, meaning generic in some Zariski open subset of the base. So this generic fiber have these properties. So the generic fiber, the Turing number is, in fact, tau min, because the tau is upper semi-continuous. And we also can consider the dimension min of the base. And since we have this relationship here, this is also achieved. So if the minimum is achieved here, then since this is constant, it should be achieved also here. So in both we have the minimum here, and then we have this formula for, so tau min can be expressed in terms of the Milnor number, tau minus, and this Q min, okay? So our result relies on this formula. So Gensmer gave an expression for Q min, okay, for the base dimension, the dimension of the base of the miniversal constant semigroup deformation, and we interpret this tau minus with the formula of CTC wall, which also was very old, but in fact, apparently it didn't appear related in the work, in the following works, to this tau minus by Tessier. Okay, so then we will go for this tau minus, okay? for interpreting this tau minus, we go to another theory of deformations, but now we are not deforming curves as a germ. We are deforming equations. So when we make an unfolding of an equation, is simply adding to the equations some parameters multiplied by some elements of the ring, such that when they are switched to 0, then I recover my curve. And it is called a miniversal unfolding when you have, I'm sorry that I didn't mention the fact. So miniversal or versal, it means that when you deform, in your deformation you have one representation of any analytical class that may appear when you deform this curve. So this deformation is versal, meaning that it's sufficiently general that you have a copy of any deformation you may do with your curve. And if this base is minimal, then it is called miniversal. So here we have also the same thing, but we know that for unfoldings, the miniversal unfolding, the dimension of the base is exactly the Milnor number. And from miniversal unfoldings, considering the polynomials or the functions, the series as holomorphic maps, then you can always get from an unfolding a deformation. So in this way, so you can, considering by maps, you can get, so you have the locus of zeros of the polynomial, which is in fact your germ of curve. And then, since any versal unfolding or miniversal unfolding induce a versal deformation, we can apply what we had before. So I wanted also here to present an example of what I am saying. So here we are having a cusp. In this here we are having that the Turing algebra and the Milnor algebra, since it's very easy, are the same. But so when you have the equation, then you have these two generators, and so a miniversal unfolding of the cusp is just adding two parameters, one for the x and one for the 1, and then you have straightforward by the construction that I mentioned, a deformation. And now the key result is to notice that the dimension of the miniversal mu constant unfolding, in fact, is the tau minus by Tessier. And we argue this so by easy facts, which says, okay, the dimension of the base of the miniversal mu constant unfolding of F, let it call theta, the theta appearing here. And so using that the miniversal unfolding is a versal deformation of this base dimension, the Milnor number, and also given that the mu constant strata of any versal deformation has the same codimension, we can take this codimension here from the deformation coming from the unfolding, and also considering the one coming from Tessier, which come from the generic one. And here, with plane curves, we know that the mu constant deformation is equivalent to a constant deformation, a deformation with a constant semigroup. And so we have this equality here, and we can see that here the tau minus is in fact the dimension of the miniversal mu constant unfolding of F. And for this, of course, there were known formulas, and this was the formula by CTC Wall and by Mattei. So in the sense of Wall, it was the tau minus was the modality, and they had this formula here in terms, you see, of the sequence of multiplicities of the resolution of the branch. So we could use this for the tau minus, and on the other side, Gensmer gave a formula for Q minus for a branch, and then we could also use Gensmer formula, and then we put them together, so like a children puzzle, and then we got our result of the formula that I showed you at the beginning. If you want further details, you can, well, you can check this reference. So thank you very much for your attention.
Okay, thank you very much, Maria, for the very nice talk. So, questions?
I can't hear you. Can you give him a microphone?
Vas a hablar, sí.
Yes, the power 4/3. Sorry, they have? Yes, I think so. That for some families, it is attained. Yes, but yes, by Dimka and Groyel themselves, they gave some examples, I think. Yes.
So in higher dimensions, you don't have this thing that topological equivalent hypersurfaces are connected via deformation. So do you expect to have something similar in higher dimensions, some bound to the quotient or something?
We are, well, in fact, you should ask this to Patricio, because he's more involved in this he's more involved in this problem. But in higher dimensions, you get more difficult things, in fact. So the topological classifications is not so easy as for plane curves. So there are more, there are different actors there, so to take into account. So Patricio shows in his generalization for general curves that you have to take into account other analytical invariants there, so, and the analytical genus of the surface and so on. So it's not so easy, but I advise you to ask to Patricio for a more precise answer to your question.
Thank you.
So thanks, Maria. So do you know something about the Turina number stratifications of the mu constant stratum? So if
yes. Well, in fact, the key point, okay, about the Turina stratifications, it's an old result, I think, by Nacho and perhaps yourself, or I'm not sure, but I don't remember all the people there. But the Turina number, it's not so subtle to differentiate the stratums. They are not good, the stratum by Turina number, because you may have very different things having the same Turina number. So the right to see when you want to stratify, and this is what we want to understand. So we know that we have a Jefez and Hernandez algorithm, but we also want, this algorithm is good because it solves the problem, it gives a normal form, but it says nothing to you, or not enough, as we wish to know about these stratums, which were, so I think that the right object to see when you want to stratify, it's not the Turina number, but this semi-module of values. So as we say, we stratify by the semi-group. In the analytical framework, we should stratify first by the semi-group of values, and of course, you have a fixed Turina number, but different semi-group of values may have the same Turina number. But you can differentiate which stratum are you, and so this is the right to see there. And this is the discrete part of the analytical classification, the first step. And then inside this stratum, it would be very interesting to look at how different there are the other. So if you have something generic there, or you have what you have about the analytical part. In the analytical classification, you have something which varies continuously. You have something that goes discrete there. So when you have a normal form, you are a little bit blind in some sense because you put zeros so as much as you can, but you don't know if this zero was some that make you to do this to this stratum or not, or it was, but because you have this continuous thing there and you can put a zero because it is continuous, and I choose a zero because it's more easy. So yes, and I think that the way of the stratification would be in this way. So.
Okay. More questions?
I want to ask a question. I'm not sure if you have already answered this, but at one point during the talk, you talk about the dimension of a mu constant unfolding, and I was wondering whether there is a module that helps you construct this mu constant unfolding, sort of like a Martinet type result.
I don't know about this Martinet type of sort.
So, the Martinet type result is that you have a quotient.
Matei, have you said? Sorry,
Martinet.
Martinet. No, I don't know. So can you explain a little bit?
So what I ask is whether you know of a module, a question module, that is finally generated and whose generators will give you the constant unfolding.
Yes, you have the Milnor algebra here. So that gives the Milnor algebra, the generator of the Milnor algebra gives you this. Okay, so in this sense you have this, and also in the Turing algebra you also have the miniversal deformation. So yes, you have this. So, and the question was, or?
Yes, if you have one question like this for the mu constant case, like for unfoldings that preserve the mu.
So yes, we have for the, and then when you switch to the, I perhaps it's the same construction. I'm not sure if I understand you sufficiently well, but when you switch to the Turing algebra, then you are making, in fact, a quotient. From the Milnor algebra, you make a quotient to make a miniversal deformation. I'm not sure if it's the same, but we can talk afterwards, so I can understand you better.
Okay, thank you very much.
Okay, pues Ignacio.
So yeah, thank you, Maria, for your talk. I wanted to ask if I understood correctly at the beginning, you said there was no constructive way or to build a curve with the minimal Turing number. That satisfies this tau min.
See, you didn't knew a closed formula for the tau minus, although you know that it was a topological invariant, but you only knew that you put this in a computer and it computed the tau minus, and okay, all the tau minus satisfy the Dimkam-Groyen question. So, but this was nothing. So,
but is that computed by calculating an actual curve that satisfies the minimal
not exactly, not exactly. Number? Okay, no, the procedure of this relies on the fact that the program puts some the program is a closed algorithm, so it's completely topologic. So from the semigroup you have a closed algorithm which says make these transforms with the elements of the semigroup, and you have this tau minus, okay? And it's combinatorial. But the proof of this, okay, sorry. The proof of this relies on the fact that this algorithm that gave Pereire is supported on the fact that all the operations that her algorithm performs are based on the fact that there exist generic elements, because in the way that you say that you are fixing some coefficients, you are fixing, others you are taking them on some open sense, and in fact you always have an open, well, you have also not open, but you have a non-empty intersection at the end. But it's a very involved proof, so I cannot say to you that I can give you a straightforward the generic element there. So.
Okay, and another question is, would it make sense to consider this as a global problem? So you have a curve and you say, I'm looking at the mu constant stratum and I want to find if there's a global representative that minimizes the Turina number at all like the total Turina number, and if you have ever.
Yes, you know, that. Well, you know that it exists, so you have in the branch case, you know that, so it is connected, Tessier proved it, so so you have this generic, in fact. So the one question is, for instance, with many branches, you also have this minimum, but are you, well, it's something that I think, well, perhaps there are very many people in the audience who perhaps know more about this, about recent developments, I'm not sure, but in the many multi-branch case, well, it's not stated that there is an irreducible component. So perhaps you stick in a minimum within a component, and it's the minimum, but okay, well, it would be interesting to have this. The minimum is the generic, so as you ask, so it's very, very interesting.
Okay. Volga?
Is there an algorithm if you have a plane branch f of x, y equals 0 to write down the versal equisingular deformation?
Can you repeat, because I missed some of the words with the microphone, sorry.
So if you have a plane branch f of x, y equals 0, you first want to write down.
Nos vamos a quedar sin café.
Out of battery.
You can write down the versal,
yes.
Versal deformation explicitly.
Yes.
How about writing down the versal equisingular deformation?
Yes,
So there's an algorithm for writing that down.
You could, yes, but you could profit from the Gensner, the Jefez-Hernandez algorithm. You could profit from it and do it.
So they write down an explicit tangent space.
I'm not sure if they didn't, because they only give the normal forms, but I'm sure that you could. I've not seen an explicit algorithm. So if you are asking me, for any curve are you asking, not for the generic one. For the generic one, the algorithm by Pereire, he also, at the end of the thesis, she also gave a way to give that what you are asking for, so to give from what will be a versal deformation, in fact a mini-versal deformation of a generic curve with this semigroup. That in general, I've not seen this written, so but I guess that from the ideas from Jefez, you could write this, but I've not seen this written.
Thank you.
Okay, just a second. About the versal deformation, so you were talking about versal equisingular deformation, I think, but the versal equisingular deformation of a plane curve, of an irreducible plane curve, I think Pierrette Casu-Nogués has written down the equation of a versal equisingular deformation of an irreducible plane curve explicitly. I don't remember the reference.
Sorry.
Just a comment. And it was just a comment about the question of Enrique and Jose Ignacio, is that when talking about minimal Turina number, there is, as Maria was saying, there is two problems, because you can think about the moduli space or minimal Turina number. If you are talking about normal form and so on, then you can look at some generic curve in the moduli. But this is one problem that is complicated. then, as Enrique was saying, is if you look at the Turin stratification, then in the minimal Turin stratum, then you can find curves that are not generic in the moduli space, which is another interesting problem, because you can use non-generic curves to compute the minimal Turin number. So when you want to generalize this to more general settings, as Jose Ignacio was saying, maybe it is a good idea to just to look at the Turin stratification instead of looking the analytic classification of curves. It was just that comment.
Thank you.
Okay, more questions?
So in the normal form theorem of Jefeza and Hernandez, that gives you a universal deformation of a mu constant, mu constant universal deformation. It is in the normal form theorem. You only have to put also the parameters at the end. So.
Thank you.
Is there some ring, Maria? Is there some ring theoretical interpretation of tau mean, for instance? I mean, the formula for the Milnor number is the adjunction formula that you use. So this means that there is conditions which are linearly independent. But you have something similar?
No, we don't have. No, we don't know it. So no, it would be nice to interpret it in this sense also. Yes. Geometrically, why the terms on
yeah, to look at some
yes.
well-identified ideal. Which
yes, we didn't see at it, okay, but it would be interesting to see this way.
Okay.
Thank you.
Okay, more questions? Sorry, no. Well, we finished, but we need half an hour to. So we will start 12:20, okay? After the coffee.
Okay, great. Great. Even
You are okay to start?
yes.
So next speaker is an advertisement.
Sorry. Just a small announcement. So tomorrow there will be a short communication / celebration in honor of Enrique and Kike and Alex. That will be after the coffee break. So just make sure you're here on time. It's not announced. It was supposed to be a surprise, so you were not listening to this. I just wanted to make sure that everybody knows about it. And it's a surprise, but not that big of a surprise. It'll be short, and it'll come before the mini course.
Okay, so Sabir Gusseinzadeh from Moscow State University, and the title is over there. So please.
Yeah, thank you very much for giving me possibility to make a talk at this conference, and this is an honor and also pleasure for me, because I know both people whose birthday we are celebrating for many years from scientific point of view and from friendly point of view, but of course my much close scientific relations and long-lasting were with Alejandro. In fact, this is our somehow cooperation now lasts for almost 28 years. So there is only one person with whom my collaboration was a little bit longer, with Wolfgang Koeberling, but Alejandro and Ignacio were also very close to that. And in fact, even our first paper appeared soon after that, and something like 26 years ago. And so after that, we worked quite a lot. And I want to talk about, from my point of view, the most exciting our result, from my point of view. So at least it is really one of the most cited results for all of us. And this is about so-called power structure. So I'll go to the presentation, some words about my talk. In fact, I was planning, when I came here, I was planning to say that this would be my first talk with a presentation. I mean, offline talk with the presentation, because I never, so I don't like giving talks with presentations, and I made some of them only when I was so during the pandemic, or when I was not able to come. No, for example, at the Nice conference, so I was forced to make presentations, and initially I was also somehow frightened that I would have to make a presentation, and you see, there is something. But when I came here, Jose Ignacio explained me that I can and the presentation was not finished when I came here, so I told that I have to work on it more. And then Jose Ignacio told, relax, you can go on with this tablet. So because of that, I decided not to throw out the part which I made already. So my presentation will be a hybrid one. So I'll discuss something on through the presentation, and then to go to the write something on the tablet. Okay, so this is about so-called power structure, the notion of power structure over the degree of variety, but even the notion of power structure is somehow our invention. Though I must say that in some sense it seems that some people understood this concept, they were attracted also by them because of its name. So how to say it, when something gets a good name, it is very important for distribution as a result. And the name is not ours. We did not find a good name for that. In the paper which we submitted first, it was called something like exponential function on on the Grothendieck ring of varieties. And probably because of that, the referee wrote, "Oh, there is absolutely nothing new." So you have, of course, so everything what is written in this paper is known as a folklore, and so the paper should be published somewhere, but not in such a good journal as the I don't want to make precise references to the journal which declined our paper, but later it was submitted to another journal. Even at that moment, the other journal was somewhat better, from at least from formal point of view. I mean, from how to say it, this impact factor, something like that. I don't. But and then it was really accepted. But the referee told that the name is not good, and they should use another name. For example, this one. And this is really we liked it very much, and we like it up to now. So the power structure is the following. No, this is not a power structure yet. So the idea which we what we wanted to do was the following. What our initial idea that we wanted to have sort of motivic version of the classical monodromy zeta function. There were some motivic versions, and there are motivic versions due to Deneuve and Lozère, which are elements of Grothendieck ring of varieties with actions of roots of unity. But we wanted to be more close to the standard concept, where it is, say, a rational function or a series if you decompose this function like that. Like just a moment. What did I do? I have to replace. Like, for example, we have this equation due to Ocampo. So here I don't want to go to details in terms of a resolution. And so, for example, we have a sort of generalization of this formula, which is in fact also, this is a generalization of the formula of Ocampo, which also belongs to us with Alejandro and Ignacio. This is for so-called partial resolutions. When you have to integrate over the exceptional divisor, you have to integrate local zeta functions like here. And we wanted to make it possible not to use Euler characteristic with values in z in the integers, but to somehow to mimic something like that, but with the ring, Grothendieck ring of varieties. And so the question was, suppose you have a series. So what is the question was, what meaning is this? And the Euler characteristic in this case has to be substituted by the universal Euler characteristic in the class of quasi-projective varieties, which is simply class in the Grothendieck ring, nothing else. So one has to answer the question, what is the meaning of this expression, or of expression like that when you have a series in with coefficients in the Grothendieck ring of varieties. I mean, here is, of course, this is integral. The Euler characteristic is here upstairs because it is multiplicative. The group where the monodromy z functions take values are is the group of rational functions with value 1 at 0. So this is multiplicative. You have to put product. And so because of that, we somehow what was necessary, we gave the following definition that what happens? What did happen? No, okay. So this is what I told at the moment is just first 3 lines of this, that it was we wanted to substitute the Euler characteristic by the class in the Grothendieck ring. And in principle, the definition of the power structure of a ring, a certain ring, is the following, that it is simply a method to give sense to an expression like that. So you take a series in T with coefficients in the ring, and you put here also an element of the ring, and you have to give sense to this expression. So when so that all usual properties, something like a times b in the power m is equal to a in the power m times b in the power m, and so on. You can imagine standard properties of the exponent hold. And of course, for the ring being the ring of integers, no one can use the usual exponent. It is simply like that. It is the formula which probably people do not remember by heart, but it can be found in many books in calculus or in more books in combinatorics. This is the usual formula for a power of a series. So we have to take sum of all k. The coefficient is sum of all partitions of k, and then you write this expression m times m minus 1, m so on, and product of ai in the power ki. Ai are the coefficients, and divide by product of ki factorial. So to work with this formula explicitly is to substitute objects here, elements of the ring, by elements of the Grothendieck ring of varieties is somewhat boring, and it hardly really makes sense. Of course, one can do something like that, but then one has to divide. So one can take that M is a class of a variety, or element of the Grothendieck ring. You can, in principle, you can write like that. One is, in this case, the class of the point. AI can be also varieties, but then you have to divide them by some numbers. No, of course, you can tensor Grothendieck ring of varieties, but by Q, but it's a very artificial thing. And the idea to make equation like that, but which makes sense over the Grothendieck ring of varieties, was the following one. Maybe before I go to the next page, I'll tell something. So when we work, what is M? This is, in some sense, this formula can be considered as the what do we want, but for a subring of so Grothendieck ring of zero-dimensional varieties. Grothendieck ring of zero-dimensional varieties is nothing else but Z. So because you have to. So what is then? What is M? M is number of elements of M. It means when you substitute points in M, you have to substitute by the variety M. What is M minus 1? M minus 1 point. Which point? At the first place we took a point. It was the second should be different from that. Then you have M minus 2. It is not written there, but what should be? You have to take a point from M minus 2 points. Which points? Which were taken at the first step and the second step, and so on. So it leads to the following expression. So if you have now, if what is I is equal to Grothendieck ring of variety. Okay, it is, of course, there should be I is K0 of var over C. I don't know how, though, of course, there is a, if I is the Grothendieck ring of complex quasi-projective varieties, one has to give sense to expression like that. Series with coefficients, coefficients are classes of quasi-projective varieties, and the exponent is also the class of a quasi-projective variety, M, and one has to give a sense to this. Of course, one has also to give sense to expression when AI is virtual variety, I mean variety minus variety, but this is much more easy, and this is not so this is not so exciting in some sense. How one can do that? I told you that one has to take points of M, then points of M without the first point, so it means that one can should take points from M, so that all sum of ki tuples from M, so that all of them are different. So it means that one has to put one has to put to take M in the power sum of ki, throw out the big diagonal, the part where at least 2 points of this sum of ki tuple coincide. This is a mimic for this expression, which is the. Then the mimic for this is obvious. It is simply product of these varieties, like here. But then you have to use to divide by product of ki factorial. But this simply means that it is possible to factorize by a free action of product of the permutation group of Ski. But here is, how to say, delicate moment is the following, that how this should act here. And the answer is that it should act in the following way, that it acts, the group Ski acts simultaneously on the factor. So M, this M in the power sum of Ki is product of MKI. And you simply take this factor, and Ski should permute the factors of it, m's here and here. So it should act simultaneously here and here, and then action here is free because all points are different. And so this is, in some sense, this is division by ki factorial. So this is the equation. In fact, initially to prove, so we, after some attempts, we found this equation. But the idea initially to prove that the equation was suitable, so to prove all standard properties of the exponential function was rather not pleasant initially, but then we at the moment found a good interpretation of this, which was permitted us to prove that this is really like that. So this was the equation which we used, and there was the very first, so some applications, first applications which we made. Then there were later there were applications of other people who were attracted by the very first application which we found in that paper was the following. We rewrote in terms of the power structure, we rewrote a certain result of Götzsche, Lothar Götzsche, who gave the generating series of Hilbert schemes of zero-dimensional subschemes of fat points on a surface. And in terms of our of the power structure, his equation could be written like that. You have to take a certain series, this one, which does not depend. So if you have consider Hilbert schemes on a smooth quasi-projective surface, the computations were only for surface, because in this case the Hilbert schemes are smooth, and then there are some methods to compute their classes due to cell decomposition of the groups of things with action of C star in the power 2. And then you have to put simply exponent, the surface as the exponent here. So this was simply first application, which was in our first paper, was this rewriting of that. Then it was later we understood that it was the power structure was not only a method to write known equations, but also to prove even new ones. For example, a generalization of that can be considered like that. If we take a smooth variety, smooth is here essential, smooth variety of dimension d, M is a smooth quasi-projective variety, manifold, excuse me, smooth manifold, it means smooth variety of dimension d, and here this is Hilbert scheme of points of zero-dimensional subschemes of length k on M. Then these Hilbert schemes are, in principle, it's difficult to compute them really, but because they are, in particular, because they are singular in general. But nevertheless, a sort of version of that equation is the following one: that one can the generating series of classes of these schemes can be written like that. One has to take the generating series of these schemes, but simply on CD, on the affine space, concentrated at the origin. So you take zero-dimensional subschemes which are concentrated at the origin, fat points at the origin, and their class, and you have this generating series, and you simply take the exponent of M in this. By the way, about the formula of Götzsche, I forgot who, but told us that somehow it was, people told that his formula was something like an exponent, but they did not associate it with expression like that. But and this is, in fact, the one which is here. This one is nothing else but the Hilbert, the generating series of classes of Hilbert schemes on C2 concentrated at the origin, like it is in this part. Now there were other. Later there were other. For example, we made similar things for proved generalizations, even in more cases, for so-called nested Hilbert schemes, in the sense of chair and so on. So I don't want, because no, I probably won't, but this is the end of my attempts to write a presentation. This was the end. So I'll switch to the to this tablet in some minutes. But before that, maybe I can tell something words about without writing. I don't think that it is really necessary to write these things. We made other applications of the notion of the power structure, in particular in the framework of the following. There was a notion of the Arbifol-Dolly characteristic, and Arbifol-Dolly characteristics of higher order. So I don't want to write, and even maybe it is good that it is not on the in my presentation, because otherwise I would be forced to explain this notion in details, and this would take quite a lot of time. And there were equations, for example, so for some sort of Euler characteristics. I mean, Euler characteristic is an additive invariant. First of all, there was an equation due to Zhu and what is? You remember better the names, I forgot again. Okay, about for the generating series of Hilbert of Hodge-Deligne polynomials of analogues of symmetric powers of varieties, reduction of a group, and we were able to give a generalization of it in terms of the Grothendieck ring of varieties. In fact, I must say that the equations in the Grothendieck ring of varieties, which can be obtained from like with the use of the power structure, probably are not so important themselves, because somehow they are, of course, interesting from formal point of view, but mostly they are interesting because one can use them to obtain their reductions for, I mean, the class of a variety in the Grothendieck ring of varieties is the universal additive invariant of quasi-projective varieties. But there are more standard, or more useful and more necessary for many things additive invariants, and probably one of the most advanced of them is the Hodge-Deligne polynomial of a variety. And Hodge-Deligne polynomial is a polynomial in two variables, and in fact all these all additive invariants, no, at least all reasonable additive invariants of quasi-projective varieties, are reductions of the class of the Grothendieck ring under a so-called homomorphism of the power structure. It means that if something is written in terms of a power structure, of the power structure, excuse me, of the power structure, this is important. I'll discuss this in some words. Maybe I'll go back to the what happens. Up. How did it disappear? Probably I made, no, okay. Doesn't matter, I'll switch to that, I promise, but I made nothing, so I was explaining that. Huh? Jose Ignacio appeared here. I didn't notice him, so Okay. Okay, so he was afraid that I would not be able to do that. He found that I was somehow analphabetic in these cases. So there is natural power structure, for example, over the ring of polynomials in two variables with integer coefficients, so that the Hodge-Deligne polynomial is a homomorphism from the Grothendieck ring of varieties to the ring of polynomial ring in two variables, and this homomorphism is a homomorphism of power structures, and because of that, each equation which we wrote can be immediately translated to an equation for the Hodge-Deligne polynomial. And for example, I told that we made a generalization which was made initially for Hodge-Deligne polynomial already, but later we made similar things for higher order Euler characteristics, which where the equations before that were known only for the standard Euler characteristic, so not in polynomials of two variables, but we wrote it generalization for the generalized Euler characteristic with values in the Grothendieck ring of varieties, and because of that, it was instantly gave a equation for the Hodge-Deligne polynomial. Okay, some more words about that equation which was disappeared because of Jose Ignacio. I must say that at the moment I made a mistake thinking that a power structure, but in some sense I would say that this should be called, from my point of view, the power structure, because I believe that in some sense with some additional conditions, this is the only power structure on the Grothendieck ring of varieties. So what sort of condition? In fact, there is another one. For example, power structure is closely related to so-called lambda structure on a ring. But there are many lambda structures, but many of them give one and the same power structure. But there is a method to so-called opposite lambda structure gives another power structure. But this power, the other power structure, which we know, is not, we call it not effective in the following sense. In the equation which was written here, in which disappeared, you saw that if you took coefficients were classes of varieties, then the result was series with coefficients also classes of varieties, not classes of the Grothendieck ring of varieties. There were no subtraction. There were only varieties. So it means that it is the power structure is in fact defined not on the Grothendieck ring, but on the Grothendieck semi-ring when we exclude minuses. Already is defined. And I believe that in some sense, if we require that the power structure is effective in this sense, then it is, I believed that it is the only one, but later my former student, Zhenya Gorsky, convinced me that one has to make make the statement more precise, to explain that one has to work in some class of power structures when coefficients can be expressed from initial coefficients by some class of operations and so on. Otherwise, it's almost senseless. So I'm not sure that I can really formulate the problem, but I believe that there must be some condition under which this is the only power structure on the Grothendieck ring of varieties. So, by the way, when did I start? I forgot. Huh? 10 minutes only. 10? Oops. Okay, then I have to, then I wanted to say some words about further development of this, further applications of this concept due to some other people, but probably I should skip it otherwise. So I'll explain you some recent application of this concept. And so one can write, there is so-called McDonald equation for the for symmetric powers of a topological set, topological space. In fact, it is like that. that if you take a topological space X, X, then the series 1 plus sum for k from 1 to infinity, Euler characteristic of skx, this is symmetric products of k, t in the power k is equal to 1 minus t in the power minus Euler characteristic of x. Here the Euler characteristic is the additive Euler characteristic, which is alternating sum of the ranks of the cohomology group with compact support. Or similar one can write the equation for the so-called configuration space of k points. So lambda xk is, you take x in the power k, subtract the big diagonal, and then factorize by sk. So the usual power structure is obtained when you don't subtract the diagonal. And then 1 plus sum of Euler characteristic of lambda k x, t in the power x, t in the power k is equal to 1 plus t in the power Euler characteristic of x. These are equations, and in fact one can write very similar equations for the in the terms of the Grothendieck-Riemann variety. So if x is a variety, complex quasi-projective variety, then both skx and lambda kx are quasi-projective varieties, and one can write the following equations: 1 plus sum for k from 1 to infinity class of skx class t in the power k is nothing else but 1 minus t in the power minus class of x. This is in the terms of the Grothendieck-Riemann varieties, which I explained. Or 1 plus sum, again the same sum of classes of lambda kx, t in the power k is equal to 1 plus t in the power class of x. So these are equations. In fact, these equations are in some sense triviality if one defines the power structures through a lambda structure, but then each of them becomes sort of tautology, but one of them, but the other one will be a consequent, will be a statement, in fact, but nevertheless. Okay, so now what happens, what I want to discuss quickly, because the time is shrinking, a sort of generalization of this object. And this is about so-called exotic configuration spaces. So suppose that on a topological space initially, you have a topological space X, and you want to consider points on them which can be colored by some colors. So say red, green, and blue, for example. Each point can be colored. But you permit that some, for example, you permit that green point can collide with red point, but for example cannot collide with it can be colored by green but cannot be colored by blue if it is already colored by green, or vice versa. And also you can permit, for example, that one and the same point is colored by one color several times. It means that it is taken like a multiple point. And so the general concept is the following: you take the lattice, the positive part of the lattice, that greater or equal than 0 in the power r. You have r is the number of colors which you use, and you take a subset here, say j, so that j is inside, in fact, this without the origin. Let us take without the origin is a subset. And then you take points which are somehow associated to each point. You associate an element of j. What does it mean? So, for example, if you have two colors, you take the some set of points here, for example, and so it is permitted that red point, for example, these are red and these are blue. Red point can be of multiplicity only 1. Blue point can be of multiplicity 2 or 1, but if it is of multiplicity 1, it has to be colored by red as well, and with multiplicities 1 or 2 or 3, and so on. So this gives a set of possible multiplicities. And so you take all the configuration space, conf. It's unordered configuration space of points. You simply take points like that, corresponding to this permitted combinations of colorings of length k. K is a multi-index, so you have to sum up all points which are there. So examples. Just a moment. What happens? Yeah, examples. If, for example, I is equal to 1, and then you take J is this, it simply means that you have one color and the point can be of arbitrary multiplicity. This means SKX. If you have one color and the J is simply one point here, it means that each point must have only one multiplicity. Then you have these configuration points of there. No other one. If you take, for example, something like that, it means that you can color each point in a way whatever you want, blue or red, but you cannot collide blue with red. It was called, by the way, the notion of these spaces, but not in unordered situation, but in ordered situation, was called exotic configuration spaces by Baryshnikov. So this he called this apartheid configuration spaces. This one. And so there are one what I just doesn't want. I see 3 minutes. Okay, so I'll now write an equation for the classes of configuration spaces in the Grothendieck-Ring of varieties. So if X is a quasi-projective variety, then all these configuration spaces of this are quasi-projective varieties as well. And one can write the following formula. Let C of Cj of T, T here is nothing else but T1, etc., Tr. You have to take is sum of all k in J. You take, simply take T in the power k, nothing else. T in the power k. T in the power k means T1 in the power k1, etc., Tr in the power kr. This is the same. So this is certain. And suppose you want to write, so look at the following generating series. Maybe it's better to write like that. Sum of all k, k. I have, of course, to delete, but it takes several seconds and I have to save my time. K in Z greater or equal than 0 in the power r. You take a class of configuration space of length k of X with the permitted permitted colorings J of k of length k, k1, etc., kr, T in the power k. The answer is a generalization of that one. You should take this series, which is series in fact with integer coefficients, and put it in the power equal to X. This is the equation which gives you the generating series of configurations and exotic configuration spaces, which are this is direct generalization of the equations which were written for the symmetric powers and for configuration space of different points. And of course this gives instant consequences for the standard Euler characteristic as well. So if you put, instead of classes, you put Euler characteristic, you have to put Euler characteristic here as well. And for example, for the Hodge-Deligne polynomial, it is the same. So this is an example. And in fact, the proof is in terms of the power structure, the proof is almost a tautology. So it's not somehow if you don't use the notion of the power structure, I would think that the proof would be rather involved. For example, initial proof of the Macdonald equation was not very simple because it relied on some computations of Macdonald of cohomologies of symmetric powers and so on. So I think that I was, yes, I am on time. Oh, great, great. As usual, I didn't use my time well enough, in the sense that I had to shrink it at the end, but thank you for your attention. And
So thank you very much, Xavier, for your very nice talk, good presentation. So this will be historical. Okay.
next, I have to make once a talk with the presentation, probably, in my life.
Okay. So questions?
In the formula you obtain generalizing from Götzsche, 1, you start with the Hilbert scheme of a manifold, and you reduce yourself to the punctual Hilbert scheme of like an affine space. What's the dimension? I mean, how do you get the dimension of the affine space that D? And how do you reduce yourself to like the Hilbert scheme of things supported more in general and scheme supported only at one point? Is it because it's smooth, so it is enough to consider just one point? Or there is something else?
No, it's, what do you mean? Somehow it means that the total generating series for an arbitrary manifold is nothing else but the generating series for one point in the power class of the variety. And yes, I understand. 1 point, no, I cannot. So why it is 1 point? I cannot answer your question. Excuse me. It's somehow what can be else? From my point of view, what can be else? Of course, you can if you work on say affine plane, you can take all the but otherwise you have take sort of. If you take a generating series for a manifold, you have to take something like root of degree m, where m is a manifold, and I'm afraid that this concept is absent, and you cannot write like that. I'm afraid, but maybe it's. Excuse me for not being.
Okay.
So I have one remark and one question. The remark is that, in fact, this is remark due to Oleg Vero about the name of the subject that not many people knew about and wanted to know about idempotent analysis. But the situation changed when the name changed to tropical geometry. And the question is, and what is the power series? The power structure.
But
what is the definition of the power
I gave
structure?
this definition. It is a method to give sense to an expression of the form 1 plus a1t plus a2t squared plus etc.
Okay, so it is not a mathematical object, it's a method. Or is it some...
It is additional structure on a ring. Where if you have a ring, you must have this additional structure, that there is a map from product of set of series times the ring to this set of series, which satisfies 7 properties. I didn't want to write this. I decided to say that these are standard properties of the exponential function.
Okay, there are more questions?
So yeah, maybe related with the other question, if, for example, you start from, say, the cusp, could you give also this Hilbert formula for the curve? Because in that case, okay, there is stratification, not only...
For curves, it is somehow, this is sort of a reduced formula, because you somehow have to take the part which is smooth, and then there is a trivial, and then you have to multiply by the one which is concentrated at the origin, and the one which is concentrated at the origin also can be obtained, can be given in sort of power structure, because it is in this case it is quotient by a group. You can consider it like that in this case. So for these singularities, you can, for such sort of, you can do that, and even for say surfaces which are with which quotient of surfaces by some groups when it is known how what is with this. We in fact we wrote some equations for invariant Hilbert schemes, and which give this. This can be written, but in these terms.
Okay, more questions? Is there some, I mean, for cases like McDonald's equation without explicit formula on the right, is there you can deduce some recurrence relation among the coefficients?
Recurrence relation.
Yeah, for instance, if the exponent will be not a variety, you will be linear.
Yeah, I understand. I don't know. We didn't think about that, I'm afraid.
Okay. Okay, so thank again to Xavier. ¿Qué tal, Patrick? Impresionante lo de los Lotus. Lo de los Lotuses, que es impresionante, todo lo que has contado esta mañana. Me ha gustado mucho. A ver si sí. Ya tengo un buen plan para la jubilación. Pasar
determine the topology, which is not really a surprise, but also the pi1 does not determine the pi1 up to isomorphism. Then there was some work by Enrique, Artal, Carmona, Cogoido, and Marcos. I think they are almost all here. They made progress in understanding this example by using the derived theory of pi1 to construct the obstruction for this example. So you stop me if I'm saying something wrong. And then, so I should mention also this. So if you combine the result of Fei and Nazir Yoshinaga, so it is known now that there is no Zariski pair up to 9 lines. So it means that up to 9 lines, combinatorics are enough to determine the topology. For 10 lines, it's still open. And then after 11, there are several examples that I will mention now. So some examples were given by the same Artal, Carmona, Cogoido, and Marco in 2005. And they show that they have, so it's real arrangement with conjugated equation, and they have different topologies. They use the braid monodromy to show that. And then we introduced, of course, there are several other results. I just mentioned some of them, but we introduced with Enrique and Benoit Gerville-Ballet a new linking invariant of, topological invariant of line arrangement in 2015, and Benoit used it to construct several examples of Zariski pairs of line arrangements. And then to finish with the history, then he wrote, Benoit and Juan Viusos worked in 2018. So they introduced a new invariant of real arrangements that is called a chamber weight. And it's closely related to the linking invariant, but they use it to produce several examples of Zariski pairs of real line arrangements. To conclude with this introduction, it is still unknown if the following invariant depends only on the combinatorics or not. For example, the characteristic varieties. So there was studied a lot by Liebgober, many people, but in particular by Liebgober and Cohen and Sushu. And so I don't know how to state it, but the main part of the characteristic varieties is determined by the combinatorics. But there are some isolated points for which we don't know still if they are determined or not. And also the Betti numbers and the monodromy of the Miller fiber. So to my knowledge, it's not known for the moment. So now I would like to go further on this notion of combinatorics and topology to explain what is my objective of. So the object of this talk is to construct a new topological invariance of line arrangements. And I would like to precise some definition before. So combinatorics is just an abstract notion. So it's a couple of LP where L is a finite set and P is a subset of P of L, which verifies the following properties. So if you take two elements, for all P there exist two L1 and L2 such that P lies in L1 and L2. And if you take two elements L1 and L2 different, then there is a unique P such that P lies in L1 and L2. So to understand this in a good way, so also it's ordered if the set L is ordered. So if you take an arrangement in CP2, a line, and you set PA the set of multiple points of the arrangement, then A is a realization of a combinatorics. So you can think as A and the set of multiple points as a combinatorics. And we say that A is a realization of the combinatorics. So the Zariski pair, for example, is two different realizations with different embeddings of the same combinatorics, if you say it in this setting. So for line arrangement, which is good, is that you have a notion of graph, incidence graph, to describe the combinatorics of line arrangement, and then you can play with graphs if you work with combinatorics. So the incidence graph of such combinatorics is described as follows. So F, the vertices are one-to-one correspondence with elements of L and P. So, and the edges, there is an edge between L and P, if it is if P lies in L, simply. So let me, I will give an example, very basic, just to fix the idea. This is the most basic I can take. So here is the combinatorics. So you have three elements in L, and P is the element L0, L1, L2, because, it means a comma between L1 and L2. And I use the notation P0, 1, 2 for short. And so this is a realization of the combinatorics, just triple points and three lines going through the point P0, 1, 2. And the incidence graph of this combinatorics is this, just simply this. So I would like to make a remark for the incidence graph. So in the future, in the rest of the talk, I will speak mainly about the reduced incidence graph, where we don't put vertices for double points. So it's just technical point, but it can be important if you go further in the techniques. So instead of working with the incidence graph, I work with a reduced incidence graph, which means that I don't take a vertex for double points. So let me explain what is the exterior and the boundary manifold, which are the main object I will use today. So if I take A, an arrangement in CP2, N of A be a regular neighborhood of this arrangement. So if you want to imagine what it can be, you can, so for each line it's a B2 bundle over a sphere in CP2. And you can imagine, if you want to imagine what happens to a double point, so you have the two neighborhood of the two lines, and they cross in a D2 cross D2. So it's a plumbing description of the neighborhood. And so maybe this is the neighborhood of the line Lj, and the neighborhood of line Li, and they cross along D2 times D2. You can generalize this construction for any multiple point, but so the exterior is the complement of this, the interior of this tubular neighborhood. It's a smooth, connected, compact four manifold. And so I would like to mention here concerning this exterior, because I will use it after, is that the homology is the first homology of this complement, of this exterior, is generated by meridians. So with one relation, so one meridian is equal to minus the sum of the others. So if you have n plus one line, then it's equal to the n, and it's generated by the meridians. So of course it's determined by the combinatorics, but we can, and the meridians are the boundary of the, so this is B2 bundle, and the boundary of a fiber is S1, which is meridian of a line. And now the main object I will consider today is the boundary manifold, which is the common boundary of this exterior. So if you look at this picture, for example, so this is the tubular neighborhood, and the exterior is outside the tubular neighborhood, and the red lines are exactly the common boundary, and this is the boundary manifold. So it's a compact three manifold, and in fact it's more than this. It's a graph manifold, as it was in the sense of Waldhausen, and it was showed by Rezebroch, Chiang Yang, and Hironaka. So also it was all studied a lot by Cohen and Sushu, so the graph structure of this manifold. So I will describe this with more detail after. So the aim today is to construct the invariant, is to look at the inclusion of this boundary manifold into the exterior, and to hope to capture some topological information from this map. So we look at this map, the inclusion map of the boundary manifold into the exterior, which is a 3 manifold, and into a 4 manifold. Of course, if you want to make algebra, we go to pi1 instead of the inclusion map. And so this map, we know to compute it by algorithm we wrote with Benoît, Gerville, Ballet, and Marco in 2050. So we know there is an algorithm to compute this inclusion map by braid monodromy. So braid monodromy is usual to compute the pi1 of the exterior, and we use also the braid monodromy to compute this map. But it doesn't give directly an invariant, and the problem is how to extract from this map a topological invariant of the arrangement. And I will be more modest at this for this talk and at this step. And instead of looking at the homotopy, I will work at the level of homology. So if we look at the map induced by the inclusion at the level of H1, so from H1 of the boundary manifold to H1 of the exterior. So there is something funny, or more or less, here is that so the boundary manifold is completely combinatorially determined because it's modeled on the graph. And so and H1 of the exterior is also depends only on the combinatorics because it's generated by meridians. But the map itself is not in general, and I will show this, that we can extract a strong topological invariant from the map itself. But one problem is that we don't have any say canonical basis of this, so we cannot play with matrices or make something usual we want. And so this is one of the problem, and so I will explain in this talk, and would like to mention it for the moment. So even if we don't have a basis, if we use the graph structure of this boundary manifold, then we can write some decomposition. So we can see that the elements of in H1 of the boundary manifold, there are elements coming from the cycle of the graph, and elements coming from the meridians. And I will explain this. But so of course, the problem is that this decomposition is not canonical, so we cannot use it directly to make a topological invariant. But I will explain how we deal with this question in the talk. Just to mention, so we made the first step in this direction with Enrique and Benoît Gerville-Ballet in 2013, and we defined the topological invariant related to certain cycle in H1 of the graph and look at their embedding in the boundary manifold and then in the exterior, and it provides some topological invariant, but we use some combinatorial, we need some combinatorial restrictions. It's not defined for any arrangement. You need to have some combinatorial restrictions. And then I would like to mention a result by Cadegan and Schippler, which is a generalization of this previous invariant we had constructed. So in different setting, but it's an extension of this. And in this talk, I propose to construct an invariant that contains both this, and it's a new generalization of these two invariants. So for this, I would like to study the structure of graph manifold of the boundary manifold. So let me explain in more details how it is constructed. So we start with the weighted graph, which we don't forget that it comes from a line arrangement. So we suppose that it is an incidence graph of line arrangement, a reduced incidence graph. And this graph tells you how to construct the boundary manifold. So it gives you the recipe. So for all vertex, you have a 3 manifold that we call MV. So for all vertex of the graph, and it's S1 Fabry space over the sphere minus disks. And the boundary of this, what we call vertex manifold, is disjoint union of tori. So it's several tori. And we glue them together, depending on if there are edges between the two vertices. Then we glue the manifold along the boundary component associated. And we glue them by longitude to meridian. So this is the sphere, the two sphere minus the disk, and then we choose now a disk into these two sphere, and we remove a disk, another one, the disk at the pole, and so it's a very special case of graph manifold. So you see that the base is a planar surface, and with no genus, and we choose a section over this SVSH. And I would like to ask something. So now, what do I have? I have a vertex manifold for each vertex of the graph. They are glued together along torides depending on the edges of the graph. And I have a section on each vertex manifold. And I would like to see how they fit together, this section. And I'm asking that, so here you have two vertices and one edge between them. So it means that they will be glued together along one torus. And I'm asking that the two sections intersect into one point in the torus, just exactly one point. So now I have a collection of sections on each vertex manifold, and they all intersect. If you change the vertex manifold along an edge, then they intersect only in one point. Okay, so now I will go to the fundamental group of this boundary manifold and explain how to use the graph structure I have described to construct a presentation of the Pi1. So I will start with the presentation of each vertex manifold. And now I suppose that, I will suppose it for all of the talks, that I have a local order on each vertex of the, so it's more than an order on the graph, but a local order. So for each vertex, I suppose that locally I put an order on the neighborhood, on the edges in the neighborhood of the vertex. And I will use it to describe the. So the generators of this, you can imagine, so if you look downstairs, you have the sphere with holes, and so you take a base point in the one boundary component, and you have the generators here, and you leave them by using the section, and you have a collection of generators, so which is so they alpha are downstairs and the beta are in the section, so lifted by the section. And so this collection of generators, and plus one, which correspond to the meridian, because you have this S1 fiber, so it would correspond to one fiber of the fibration. And the relations are not very surprising. So all these generators commute with the fiber. It seems clear, and the product of these generators is equal to the boundary with the converse. So it's 1 over the boundary component here, corresponding to the homotopy relation in this sphere. Okay, so usual relations in the. Okay, so now I would like to emphasize in something in this picture is that. This is the same picture as before. So you have a sphere minus holes. You can think downstairs or upstairs with the section, and you take a base point, and I describe the generators by using these lines. In fact, I use them to describe my set of generators, and these lines relate the point of the boundary point of the vertex manifold to the others where they will be glued, and so I let you imagine that in fact this is a part of the graph. Corresponding to around the vertex and the part of the edges that going around the vertex. So in red here, it's a part of the graph in the section, in the vertex manifold. So if I glue all of them, what I pretend is that we have constructed an embedding of the graph into the graph manifold by using this, because it's a definition, so we call this a graph embedding. So it respects the graph structure because it's embedded part by part with respect to the graph structure, and with the local order because we put an order here, we give the numeration of the boundary component. So I will call this a graph embedding, which is an embedding of the graph into the full graph manifold. And I will use this to describe the presentation of the fundamental group of the full graph manifold, so which is mainly due to Westlund and Cohen and Suciu. So we start with the graph. So the data to construct this presentation are this graph embedding that I used locally, and now I will use it for the full boundary manifold. And I take a spanning tree of the graph, and I suppose that the graph is oriented also. So the generators are of two types. So there are the local generators, which correspond to all the vertices manifold I have considered. Just one point is that I have to, so they are located in the base point where in each vertex manifold, so you have to take care about the base point. So take a path along the image of the spanning tree to the corresponding vertex V, and go back to the base point, which is given by the root of the spanning tree. So we have now one base point for all the manifold. And also, you can consider the edges of the component, the complement of the spanning tree in the graph. So I will make a picture here. So here you have in black, it's your spanning tree. So this is a part of the graph. R is the root of the spanning tree. V and W are some edges. And in red is one edges which is not in the spanning tree. And we can make a pass here in the pi1 of, so this make a generator of the pi1 of the graph manifold. By using, so for each edge, we have a pass and a generator in the pi1 of the complement, of the boundary manifold. So there are some relations that I will not state here because it's technical, but there are the relation induced by the local relation on the vertex manifolds and some relation coming from the graph. So the first observation is that this presentation, so I used the spanning tree and a graph embedding to construct it. And it depends only on this choice, but not on the graph embedding. So if I change the graph embedding, I will get exactly the same presentation of pi1. So it will be an important point later. So now, as I said, I would like to understand the homology, first homology of the boundary manifold. And so I will use this, what I described on pi1, to understand better the H1 of the boundary manifold, which I recall is a graph manifold, 3 manifold over the incidence graph of the reduced incidence graph of the arrangement. So let me start with an observation, is that there exists a continuous map on this graph manifold into the graph, which is unique up to isotopy. And for this, we contract the fibration for each vertex manifold, and then we glue them along a torus cross I for each edge. And then we construct a natural map from the graph manifold to the graph itself. And this induces a map at the level of at homological level from H1 of the graph manifold to H1 of the graph. And now I consider this group. So I will explain you what is the motivation. So C0 of gamma is just the group of zero chain of gamma, and it's generated by all the zero chain. And we call V of gamma, so the certain quotient of C0 of gamma, so coming from the gluing of the the vertex manifolds. So I don't go into details to this formula, but let's have in mind that if M is gamma is the boundary manifold of a line arrangement, this is simply this group V of gamma is simply the H1 of the exterior of the arrangement. So what is the interest of this definition is we have a pure intrinsic definition of what is the H1 of the exterior by not considering the exterior. So for the moment, I'm working with the boundary manifold, and I can define what we had in mind as being H1 of the exterior generated by meridians as this group, which is purely defined from the graph. So I can, it makes my construction intrinsic from the boundary manifold without considering the exterior at this time. So there we have the following result. So we start with graph embedding, and we say that it induces a section from H1 of the graph to the H1 of the boundary manifold, say, and such that this exact sequence split. So here you have the map C star that I have defined previously, and it says that H1 of M gamma of the boundary manifold is the direct sum of V of gamma. So that I recall is just the H1 of the exterior, isomorphic to the H1 of the exterior, plus H1 of gamma. So we have a decomposition which is not canonical, but induced by the choice of graph embedding. So this is the spirit of this result. And now from this observation, I will define an invariant of the graph manifold. So it's a combinatorial invariant of the arrangement as follows. So let me give the definition, and then I explain where it comes from. So it's a quotient of the map from H1 of the graph into V of gamma, which is the isomorphic to the H1 of the exterior, by a group generated by elements like this. So where gamma I is the embedding of a graph. So we take two embeddings, gamma 1, gamma 2. So they are embeddings of the graph into the boundary manifold. And this induce gamma tilde 1 and gamma tilde 2, and we compose with maps from H1. So we get elements. So if we compose, we get element of H1 of the graph to H1 of the exterior. And we take the quotient by this subgroup. So why is this, we do this definition, is as follows. So suppose that you have a line arrangement, and take, now M gamma is really the boundary manifold of the line arrangement, and you take I star, the map induced by the inclusion from the boundary manifold to the exterior, induced by the inclusion. So the map I promised to study in the introduction. And so you have this map, so this, which is induced by the inclusion of the boundary manifold to the exterior, and a graph embedding. So the choice of graph embedding induce a map from H1 of the graph to the H1 of the exterior, and this is what we would like to study, because we would like to study the images of the cycle of the graph into the exterior of the arrangement. And by construction, of course, this composition may depend on the graph embedding, because it depends on how you embed the graph in the boundary manifold, and then how you see it in the exterior. And the way we use to not, so that it doesn't depend, we take the quotient by difference of two such choice, and we make a group, and then it doesn't depend on the choice. So we just make the construction for that. So if we have a group which is purely combinatorially defined. I mean, not purely combinatorially, but just in terms of the three manifold. Now, not involving the exterior for the moment, but the exterior, the inclusion map is an element, gives an element of this group. So let me be more precise on the definition of the invariant now. So we suppose that we have an ordered arrangement in CP2, and we suppose that we have this local order around this, all the vertices. We look at the map induced by the inclusion in homology, and we say for any embedding which respects the local order, that the following gamma is independent of the choice of this of gamma. So let me be really to emphasize on the details. So this group gamma is what I call the graph stabilizer just before, depends only on the combinatorics and is defined from the boundary manifold. But the element here is associated with the image in this group of the inclusion map, is the topological invariant of the exterior, and it captures some topological information. So we have this theorem. We say that if A1 and A2 are two ordered arrangements, then there exists an homomorphism preserving the order and the orientation. If there exists, sorry, with the hypothesis is this, then the group are equal, and more than this, this invariant are equal in the group. So they are the same element in the group. So let me say it again to resume. So I have constructed a group of maps associated to the boundary manifold, to the graph, in fact directly from the graph, so directly from the combinatorics. And the invariant is an element of this group. So if we want to compare the invariant, we first have to compute this group from the combinatorics, and then to compare element. So the point is that, of course, with my definition of the group, it's not very easy to compute, but one of the parts of the result is that we get some combinatorial description. So I don't know how much time do I have. So okay, maybe it's too late to go with technical details, but just to, okay, I'm not going into the details, but just to explain you. So in fact, the group G gamma is a group we are working with. It can be is a quotient by definition of the map from H1 of gamma to V of gamma. And so you can see that there is a commutative diagram, and which induce a natural map from C1 of gamma, so the one chain of gamma, the edges mainly, and the zero chain, so the vertices, into the homomorphism, so using these commutative diagrams. And we consider a subgroup of this generated by some maps. I don't comment the way they are constructed, but they come from the gluing of the section when you construct the boundary manifold. And we get that this group, the group we are considering, so G gamma, is a quotient of this by the image of this. And what is really the interest of this construction is that this is a purely combinatorial description of the group, and it's easy to compute it with the computer by using. So we have really a presentation of the group with the graph. So it's really with the graph we can construct and compute the group directly. And of course, to compute the invariant itself, we need some more. So we use the braid monodromy, of course, because it captures some topological information. So, for the example, so we compute it for the MacLane arrangement. So the MacLane arrangement. So as you can see, it's not a basic example now. So we can have a very intricate graph. So this is a graph of the MacLane, so-called MacLane combinatorics. So you have different ways to define the MacLane combinatorics. Are more nice way to define them by the graph. But so and there are two realizations: Q plus and Q minus. And if we take some local order on each vertex, then we compute the invariant and show that it is. So the group, of course, itself is the same because it's determined by the combinatorics. But the invariant as element of group are different. And it proves that it does not exist homomorphism of the pair that preserves the order of the lines. And last thing, so there is some example. So Benoît Gerville, Ballet, and Adrien Rodot computed in some the invariant. Yes. 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 Did I forgot to say? Okay. Thank you. No. It's no. With the order and the orientation, you're right. So thank you for the comment. Yeah. And so I will not comment it more than so they computed the invariant in some example with combinatorics with 11 lines and which have 4 different realizations, and they show that the invariant take 4 different values, and so it's a Zariski 4 replay. I don't know. So Zariski pairs with 4 members. So I think it's all. It's okay. So I finish.
Okay, thank you very much for the very nice talk. So, questions?
So it's more a remark than a question. So one of the points is this stabilizer graph is usually big. So it depends only on combinatorics, but it's big, and so it's almost always free. But so I think the smallest combinatorics where it has torsion is MacLane's combinatorics. And actually, so when you said they are not only different, but the difference is exactly a 3 torsion. The difference of both is a 3 torsion is a 3 torsion element. So this is so actually this is more or less to show how it works, because of course already Rybnikov have proven that they were not. But then thanks to Adrien and Benoît, so
yeah, no examples. Yeah. Well, the previous one does not. Sorry.
And I think the example of Adrien and Benoît, it was not recovered by other known invariants till now.
No.
All this construction was not for line arrangements?
For the moment, yes. If the question can be extended to plane curves, yes. But of course, you have more generators in each one of the boundary so that comes from the genus of the surface. So for the moment, we did not. So officially, I guess yes, it's possible, but we did not make it.
Thank
you. Okay. More questions?
Benoît, have a question.
So I conjectured that for the I invariant and for the invariant of Cadogan-Schleiper, we cannot distinguish the topology when the invariant take value in the free part of the group, and only the torsion can distinguish the topology. I know the opinion of Kike about this conjecture, and I would like to have your opinion about it.
So I don't have any. I just can observe, like you, that in the examples we know they are all distinguished by torsion part of the group. But even this I don't understand why. No, I don't know.
Okay, so the second question was: do you think that we have something similar with this invariant, that there is no topological difference on the free part? But I think you
no, I don't know.
Yeah,
no, I don't know.
Okay. Thank you.
So effectively, I don't agree with your conjecture. My degree of non-agreement is decreasing from the time. So in particular, in 2009, here, so Fan from Taiwan, he drew an example of arrangement that for the moment we have been unable to do it. And okay, I thought that we have distinguished with this invariant, but this is what happens when you make mistakes in the computation. And so thanks to
we might work with the twist methodology by representation of the Pi1. So maybe it offers many opportunities to get stronger invariant, and maybe with for the fan, it will be the next step. So it's just the beginning of construction.
Thank you for the talk. I just wanted to ask if you ever tried anything more or less like what Alex was talking about for rational arrangements, like if you have, I don't know, lines and conics or anything. Like is genus the obstruction to do this?
Yes, maybe. No, we did not try. I guess it would be possible, but just we have to.
Sure.
Yeah. Of course, it could be possible.
There is a generalization for the I invariant. I did that with
rational curves?
With any for any curve.
Yes, sorry, yes. By you and Jean-Baptiste Meilland. Sorry, I forgot to mention this. Yes. Not for this one, but for the leaking invariant. Yes. Yes.
Well, one way to give a linear arrangement would be to start with infinitely many points, not all on a line. Okay, and take all the lines defined by two or more of those points. And just from this point of view, there is a configuration of points with few ordinary lines. Ordinary means having only 2 points at that. Of course, there is more intersection points. Maybe this in this case, it's interesting is to look to the samples with relatively few ordinary lines. So maybe it will be interesting to.
Okay. Thank you.
To improve the strategy. This is just the masking problem.
Okay.
So thanks to the speaker again.
1, 2, 3, 4, 5, oui. Pero Lille, ah, muy bien. Mucho fui yo a Lille cuando estaba ahí Alberto Rosa. Pero años y años. Ah, sí, sí, no sabía. Lo veía, me reunía yo más con él cuando estaba en Lille, que ahora está en Cuernavaca, a 80 kilómetros.
Cuando quieras, ¿no?
No, estudió que ojo meneado. Ah, pero no habías oído esa. Ya podemos empezar. Good afternoon. Welcome to this Tuesday the 13th afternoon talk. And we start with this talk by Pablo Portilla Cuadrado, in joint work with Guadrun Sigurðsson. Okay.
You can ask him later. If this is correct.
from the Lille University, and he's going to talk about vanishing polyhedrons for plane curve singularities.
Thank you. So I just wanted to say a few words for Kike and Alex. So I've known them since the beginning of my mathematical life, and I have many good memories with them. I remember the first. So I met Alex at the masters. He gave me a course on homological algebra, and I learned a lot. And I remember, like Kike, since the beginning of my thesis, giving courses, and even sometimes I remember I would take the train early in the morning and go to Zaragoza and asking a lot of questions, and then go back at night, and then yeah, and I even value more about that now, because now I know that professors are very busy people. So using that time with being so generous with the students is great. So I was looking for a lot of pictures, some pictures to share with you, and I didn't find any, which is weird because I've been with these people in many different places. So I started asking Juan and Patricio if they had any pictures of you with me at some point, and also they didn't have any pictures. But I realized that Juan is your student and Patricio is your student, and you almost look the same. So I put this picture, and then after several hours of Photoshop, I did this. You can see there's almost no difference. So I thank you for everything. So let's start with the talk. So I'm going to talk to you about the motivation of our work, and the motivation is the following. So we start with a complex analytic map, and we consider the associated Milnor fibration over the puncture disk. And we have the classical theorem by Milnor, with the F has an isolated critical point. The Milnor fiber has the homotopy type of a bouquet of spheres of dimension half of the Milnor fiber. So the motivation is like, okay, it has the homotopy type, and maybe using some general theorems for topology, you can find some set that realizes this, but the goal is to find a set that realizes it with some geometrical meaning. So construct a spine, and a spine for us is going to be something that if you remove it, you obtain a Kollár neighborhood of the boundary of the Milnor fiber. And we want to construct the spine realizing the vanishing topology, but we also want the spine to have some regularity, so prove something about the topology of the spine. And we also are interested in constructing a spine simultaneously for all Milnor fibers, in such a way that hopefully when we construct such total spine, we should be able to obtain some information about the monodromy. So this is the goal that we have in mind. And if we talk about this type of problems, like we should talk a little bit about previous work of Le. So Le wrote a paper in 1988, and later he wrote another paper with Menegon, with Aurelio Menegon, in which they gave details of the theorem stated in 1988, and in a general setting for X complex analytic space and F with satisfying some mild properties, they constructed a spine, but they were not. Their techniques do not allow, in particular, to construct this spine at the same time for all Milnor fibers over a circle, for example. And also, the constructing polyhedron depends on several choices. And we were interested in producing an object that is as canonical as possible, or so that you have to make as less choices as possible. And we'll see at the end of the talk how we arrive to some sort of solution in that sense. So our setting, we restrict to the case of plane core singularities for the moment, and we drop the condition of isolated critical points. We just allow F to have non-reduced components, and just think that the Milnor fiber of a plane core singularity, even if it has non-reduced components, it is still a surface with boundary, and all surfaces with boundary are homotopically equivalent to a bouquet of circles. So still, this question makes sense. So there is no restriction to attack this problem. So we are the starter point of our work is an idea by Norbert Campos. So let's go through that idea, and let's see how we developed. We push further the idea to give a solution. So just fix a plane core singularity. And now we consider the following. We take the unit radial vector field on the puncture disk, so pointing inwards. This is the unit radial vector field, the pointing inwards. And now we want to lift this vector field in such a way that if we are able to lift this vector field and we integrate this vector field, we should obtain, at least in theory, a collapsing map. So a map that sends Milnor fibers to the central fiber. So in order to lift vector fields, we need to put a connection. So we put the following connection. So this is something called the symplectic connection, which is just is the symplectic orthogonal to the so it's the connection given by the line field, defined by taking at each point the symplectic orthogonal to the tangent plane to each Milnor fiber. So omega here is the standard symplectic form in situ. So this is what I just said. And now just as an observation, if we change in this definition omega by Riemannian metric, because of the Kähler structure in situ, these spaces are the same. So symplectic orthogonal can be changed in this case by Riemannian orthogonal. There is nothing particular about more particular about the symplectic form than the Riemannian form. And also, well, this actually gives you a connection. So now we have a vector field, a connection, we lift the vector field. And it just happens that it's not difficult to prove that if you lift the vector field R using this connection up to multiplication by a positive real function, so something that has the same integral curves, this is the vector field that you obtain. Something some people refer to this as the complex gradient of the function. So here fx means taking partial derivative of f with respect to x. and x and y are the coordinates for C2. So okay, so we integrate this vector field, even if it's not exactly the lift, we're just studying the dynamics of this vector field. We integrate it, and using some work of Lojasiewicz, we can prove that this actually defines so everything behaves nicely. There are not trajectories that escape, and everything goes to the central fiber as expected. And so we have a map that sends Milnor fiber ft, so over the point t, to the central fiber curve, and says like the part that is sent to 0. So this is just making explicit that we are studying this set. So we want to study the part that the collapsing map sends to 0. So now we have a dynamical system problem, which is the following. We have a vector field, and we are interested in studying what is called in dynamical systems the set of separatrices of this vector field at the origin. So it means that the trajectories of the vector field that converge to the origin in situ. And we want to study this set that can be very complicated in general, and we want to study the intersection of this set with each Milnor fiber. So this is the expected spine. So this is the original idea by Acampo, and let's see how we pushed this idea and how it diverged from the original idea of Acampo. So what this is just some representation of what's going on. So imagine that, for example, we take this plane curve, and I'm just doing the real picture here. So I just took the vector field psi and I normalized it to have a nice picture. And here we have the central fiber, is that these two lines, and this is the origin. So now, if we look at the Milnor fiber, we see how the Milnor fiber goes to by the flow to the central fiber. And if we look at the set S, we see these two lines, which are the two trajectories, or the four trajectories in this real picture that go to the origin. And we can see here, like this point and this point would be the spine for this Milnor fiber. And of course, you can imagine this the complex picture by considering like the circle that goes from this component to this component, and the circle that goes from this component to this component. And we would have a cylinder, and you would find a circle in that cylinder that is contracted to a point. Of course, this is a easy situation. So in general, we don't expect to just draw a vector field and do and talk a little bit and conclude something so easy like this. So something needs to be done. And what do we do? So we want to study the set S, which is, as I said, in general a complicated set. So general principle in singularity theory, we have a complicated set. Let's blow up and see if we get to a simple, more simple set. So this is the strategy that we follow now. We blow up, we rescale. I will rescale the vector field. I will make a sense of that now, and we try to extend the vector field over the new exceptional divisors that appear after blowing up. So what does this mean? So what it means is the following. So imagine that we have here our curve C. This is the curve C that we are studying, and S is the set of trajectories that go to the origin. So here I draw some 4 trajectories that go to the origin. And then we blow up, and hopefully, if we blow up enough, we will have that these trajectories that went to the origin now would go to some points of the exceptional divisors. Hopefully, they meet the exceptional divisors transversely. And furthermore, part of the strategy is the following. Maybe rescaling the vector field, at least locally, we are able to extend the vector field over the exceptional divisors and produce a vector field that is defined on the exceptional divisors and satisfies properties such that the zeros of those vector fields are precisely the points where the separatrices arrive, or the street transform of the separatrices arrive. So let's see if this is possible or not, or what are the obstructions to carry on this program. So let's do for the first blow up and see what happens. We take the first blow up, called pi 0. So here we have the total space Y, the street transform of the curve C, called C tilde, and this 0 is the first exceptional divisor that appears on the first blow up. And now we're going to look for some function, some real analytic function, or that takes positive values in such a way that if I multiply the pullback of the vector field by pi by that function, I can extend it over the exceptional divisor, or at least the exceptional divisor minus the state transform. Okay, so when I put this little circle, it means I'm removing intersection points with other exceptional components, as usual. So we obtain this first theorem, which is, okay, if you take the square distance function and you rescale the vector field by the square distance function, you take the pullback of this vector field, and this extends to all this space. So this look that this includes a D0 circle, and to give a real analytic vector field that is tangent to the exceptional divisor. And furthermore, if we select the metric, you have to know that you have to recall that even if it's not explicitly written, the vector field depends on the metric. It's a gradient. So if we choose a generic metric, so here I use the term linear metric. So linear metric means the following: you start with a standard metric on C2, and now you take a linear change of coordinates, and you take the pullback metric given by the new coordinates that arise after changing coordinates by that linear change of coordinates. And so this set, all the metrics that you can reach doing this linear change of coordinates, this is what we call linear metrics. So there is an open dense subset of linear metrics in such a way that if you pick any metric there, the restriction, so the restriction of this vector field to the exceptional divisor, it's a Morse vector field. So it means that it admits a potential which is a Morse function. So actually, you can find a function, and the vector field will be the gradient of that function with respect to the Fubini static metric on CP1. So we have this very nice situation on the first blow up. So we just we become very happy and say, okay, we just need to blow up more and do the same. We'll find maybe the function will be slightly different, but we blow up again, and we will be able to re-extend the new vector field over the new divisors. So let me just I have forgotten that I had this picture here. So let me just tell you, this is exactly what a representation of what the theorem does in this particular case. For example, you take this is the Morse singularity, and when you blow up once, you obtain this CP1. This is the D0 circle. And it happens that when you extend the associated vector field, what you obtain is one saddle point, one repeller, and near the intersection points with the two strict transforms, you have sinks. So this is we will go back to this picture later, but for now, see that we have we're able to describe this vector field nicely here, and we see that we have saddle points and fountains, and sinks only at the intersection points with the state transform. This will be a general rule that you will not find sinks in the interior points of the divisor, only saddle points and fountains. So the problem is not solved. Like there are still complicated sets that arrive at the intersection points, and obviously we try to, as I said, we try to iterate the process and see what happens. Any number of blowouts. Everywhere where the state transform passes, you find a sink at any stage of the resolution. But I still haven't got to that point. This is so we try to iterate the process. And, well, the same strategy happens to not work, because it happens that if you do a very simple example, and maybe you will be happy because you think it still works, but if you do a slightly more complicated example, you find that it doesn't work. And what happens is that sometimes when you try to extend the vector field, it depends on which direction you are approaching the exceptional set, the extension is different. So when you have this kind of phenomena, where the things depend on which direction you approach the central divisor, you have another tool, which is the real-oriented blow-up. So we take the real-oriented blow-up of the resolution space Y along the exceptional set D. And so I think it would be very optimistic to think that everybody knows exactly what is the real-oriented blow-up, so I'm going to give some intuition about the real-oriented blow-up. And maybe if you don't understand it after my intuition, in the talk tomorrow by Javier, he will give probably more intuition. He's also, so he will also use this space. So the intuition is the following. Take polar coordinates and allow the radius to be 0. This is what we do with we take the real-oriented blow-up. So let's do the real-oriented blow-up of C at the origin. So we take C, we take the origin, and we take polar coordinates, r theta, and we just allow r to be 0 as well. And the corresponding space is something that has boundary. So it's this thing that I call C rho. So this has boundary, and the boundary gets collapsed to a point by the real-oriented blow-up. And well, one interesting thing that the real-oriented blow-up does is that it resolves the indeterminacy of the function argument of z. Here, the argument is not well defined at the origin, but here we have the argument well defined everywhere. Okay? So what do we do? Well, we take the real-oriented blow-up. So we take a resolution. This is some resolution, and we just give we name the divisors di. So this would be the vertices of the dual graph of the resolution. This is some index set w. And now we take the real-oriented blow-up of y along di. So we take one of these di's, and we take the real-oriented blow-up of y along di. And you can think of these as this is some space that, as before, is going to have boundary. The boundary is going to be precisely di rho, and di rho parameterizes the oriented real lines that arrive at di. So if you want to give coordinates to these, what you would do is you would take coordinates uv such that u equals 0 defines di, and then you apply to this coordinate u what I did before. You change u by r comma theta, and you allow r to be 0, and you cover by these charts, and you get the real-oriented blow-up. And what you do, you take the real-oriented blow-up of each of these spaces, and you take the fiber product, and you get what is called the real-oriented blow-up of of y along d. So this is a manifold that is no longer a manifold with boundary, but it's a manifold with corners. You have corners at the intersection points, at the tori that come from the intersection points of di and dj, the two different divisors. But it has some nice properties. Let me just explain this diagram a little bit. So here is the function we started with. Here is the resolution, and here is the real-oriented blow-up. And this is just how I call the composition of the real-oriented blow-up and the resolution. And here is the map that I described for you, sigma prime. It happens that the real-oriented blow-up is functorial. So this function is well defined. And so now we have, recall that here we have a manifold, which as a topological manifold has boundary, as a smooth manifold has corners. So this function f rho sends the boundary of this topological manifold to the boundary of this. So this is what is written here. The boundary of this manifold, recall that is the exceptional set, the d rho. And here, if you restrict f rho to d rho, you get a map over the circle. And think that if you move a little bit, instead of taking this circle that we can think of as, so we can think of this circle as the circle of radius 0. If you take another circle, a little bit bigger, positive radius, then f rho describes the Milnor fibration. It just happens that this map naturally defines also a C0, a topological fibration, that it's equivalent as a C0 local integral fibration to the Milnor fibration at radius 0. Sorry, to the Milnor fibration, and this is called the Milnor fibration at radius 0. So this space was used by Norbert Acampo, and actually he modified the space in order to put a smooth structure on it. But we just work with this space for this moment. So over an angle theta, so now theta moves here. Over an angle theta, we have a decomposition of the Milnor fiber into several pieces. So let me just explain what are these pieces in the next slide. Okay, so f theta is going to decompose in several pieces that are parameterized by the same index set that parameterizes the exceptional divisors of the resolution. Okay, so just take, for example, this singularity that has this resolution, dual resolution graph, and I name the divisors in the order they appear. So this is the first divisor that appears in the first blow-up. This is the second, the third one, and the fourth one. So this graph here represents this space. So we have one sphere. So we have 4 spheres that are intersected according to the intersection diagram of this graph. And here we have a little disk that corresponds to the strip transform of the curve C. And so if we see what lies over when we take the real-oriented blow-up along this particular piece, for example, so this is going to be a 3-dimensional manifold because it's the boundary of a 4-dimensional manifold, and this 3-dimensional manifold is naturally fiber over the circle, and so each of the pieces, after taking the real-oriented blow-up along the whole union of divisors, each of the pieces is going to be can be naturally identified with a submanifold of the Milnor fiber. So, for example, this piece would correspond to this surface of genus 3 and 8 boundary components. These would correspond to this surface, which is like the disunion of the disks. Here we have, corresponding to this piece, the disunion of these 4 cylinders, and here we have these 4 disks. So this is this has the topology of the Milnor fiber. Okay, so now we have this description, and we go back to a problem. We recall all the time that we had this problem of extending the vector field over the exceptional divisors. So we were stopped by this problem, and now we constructed the real-oriented blow-up, and we hope to extend the vector field over the boundary pieces, and why not? Maybe even get that the vector field is tangent to each of the Milnor fibers at radius 0. So let's see what we are able to do. So let me just do again, go back to the previous example. If we had remember that we had this vector field, it had 2 singular points. One was a saddle point, another one was a repeller. And when we take the real-oriented blow-up and we restrict it to one of the Milnor fibers, the Milnor fiber is going to look like this, which is the cylinder. And now one can check that the Milnor fiber in this piece, sorry, the real-oriented blow-up on this piece is a double cover. So here we can just take the pullback of this vector field, and here we're going to see like 2 repellers and 2 saddle points. And here I drew a new line, which is I took the stable manifolds of the 2 saddle points. If you take the stable manifolds of the 2 saddle points, because here there are only attractors, they necessarily have to go to one of the repellers, and so we see here that a spine, a polyhedron appears. Okay, let's see if we can repeat that picture in general. So here we can see again what would be like this would be the Milnor fiber at positive radius. So the cylinder that is outside is the Milnor fiber at positive radius, and here we see like the vector field that we constructed that necessarily is transverse to the Milnor fiber at positive radius, arrives to the Milnor fiber at radius 0, and after rescaling the vector field, it extends tangentially, and this would be like the 2 repellers and the 2 saddle points. So this is the picture that we have to have in mind. Let's see how accurate is this picture. So now, before finishing this program, we need a few ingredients. So let me explain to you how to choose a polar curve for each divisor that is not the first divisor. So we do the following. Take, for example, again, this example. We take the resolution, and let's see, suppose that we pick a vertex that is not 0. So we pick either D3, D2, or D1. So now we take the connected component of the dual graph of the resolution minus the first vertex. So 0 is this vertex containing I. So I is either 3, 2, or 1. And in this case, there is only one connected component, so it is this one. And we just observe that D0, the divisor that appeared first, is in bijection with directions in C2. So what we can do is we consider the tangent of the curve C corresponding to this connected component. In this case, this is irreducible, so there is only one tangent. This is the tangent y equals 0. And what we do is we take the partial derivative of f in the orthogonal direction to this tangent. So if we have the tangent y equals 0, the orthogonal direction is y. So we take the partial derivative of f with respect to y, and we obtain this equation. So this gives a polar curve, pi, which is defined by fy equals 0. So let's see what happens with this polar curve. Well, in this particular case, the strict transform of this polar curve passes through this divisor. So we observe several things. First, like each connected component of the graph minus the first divisor selects the same polar curve. So in this case, D3, D2, D1 select the same polar curve. It could be like many other branches here. But the strict transform of the curve P does not necessarily pass through all these divisors, passes maybe through some of them. And also, the minimal resolution in general does not resolve these polar curves. So because we are interested at the behavior of these polar curves near the divisors, we're going to take resolutions that actually resolve all these polar curves. So work by Tessier proved that there exists a Zariski open-den set in CP1 in such a way that if I take the polar curves resulting of taking partial derivatives in those directions, the directions contained in this Zariski open-den set, then that family is equisingular. And so what we use this result to select a metric in such a way that the polar curves that we choose are always generic in that sense. Okay, so we fix a new open-den set of metrics that satisfies the property that all the polar curves that we choose are in the Zariski open-den set given by Tessier. So we fix as metric, and we consider resolutions that resolve also those polar curves. So for instance, you can always take the resolution that resolves the Jacobian ideal. But the important thing is that we are taking resolutions that resolve those polar curves. So now I gave you a way of, if you give me a plane curve singularity, and you give me the minimal resolution of this plane curve singularity, you choose one vertex that is not the first vertex, and you know how to produce a polar curve. Okay. So let me give you a few more ingredients. So this is one ingredient. Let me give you another two ingredients, which is just some numerical invariance. So let me define some numbers. So mi's, these are the multiplicities of the total transform of f. C0i's, this is the multiplicities of a generic linear function. This is something called the coefficients of the maximal cycle. The numbers C1i, they are defined using C0i and the canonical divisor. So we take if the canonical divisor has classically written the coefficients like this, nu I minus 1, then C1 satisfies that is nu I minus C0. And one can check that this number is also always positive, non-negative. And Pi is the vanishing order of a generic polar curve. So these polar curves were always were equisingular. So the ones that are in the given by the work of Tessier, so they have these well-defined numbers. So okay, so if you don't know many about these numbers, you can just think that these are numbers that can be easily computed from the resolution process. And from these numbers, we cook two other numbers. One is the tau I that we call radial weight, and bar pi I that is called polar weight. It's just this is the important thing of this slide, is that we are able to compute two numerical invariants from numerical invariants that are very easily computed from the resolution process. Okay, so we have polar curves and we have these two numbers. So let's see what is the theorem? How can we extend the vector field over the Milnor fiber? So we extended already to over the first divisor, and what we find is the following. If we take, so remember this is the composition of the reoriented blow-up with the resolution, and we take the pullback of this function. So this is absolute value of x to the power tau I over C0i. So here coordinates are chosen without changing the metric in such a way that x is orthogonal to the tangent, to the tangent corresponding to the divisor di. But you can just think that x is some generic linear function, so it naturally vanishes with order C0i. So we take this, so we are just rescaling our vector field, and this vector field extends over over the corresponding boundary component of the reoriented blob, DI rho. And its vanishing set is not just anything, it's particularly the intersection points of DI rho with the strict transform of the polar curve PI rho. So if the polar curve passes through that divisor, there are zeros. If not, there are no zeros. Okay, and furthermore, as I announced before, like this vector field is not only tangent to these three-dimensional pieces, but also tangent to the Milnor fibers at radius 0. And if you remember before, I said that the vector field sometimes cannot be extended to over the exceptional divisors. So sometimes we needed to do the reoriented blow up, but it happens that when var pi, this order invariant is 0, and precisely when this only when this is 0, we can also extend the vector field over the divisor. Here, I'm not taking the reoriented blow. This is just the resolution. So when var pi is equal to 0, and this defines a very important subgraph of the resolution graph, the union of those vertices where var pi I is equal to 0. Over those divisors, we can extend the vector field, and also we get a vector field that is tangent to the divisor and whose vanishing set is the intersection points of DI and the polar curve PI. Remember that we resolve, so these intersections are transversal. We solve the PIs. So this should be the strict transform of the curve PI. So, okay, we have a vector field that has some isolated zeros. What are these zeros? Well, these zeros are precisely saddle points, not just anything. So, the vector field, when we extend it over these pieces, acquires some zeros that we are able to select, and these zeros are saddle points. And so this is the picture that you can think of. So here we have a piece of the Milnor fiber, d rho I theta. So this is the Milnor fiber over the angle theta, and this is just a piece. And here we found a zero. So we see that there is a saddle point here. And we think now about the trajectories. We were studying the set S, so we think, okay, now we have a zero, and this has to attract some of the trajectories of the separatrices. What is this? What is this blue space that takes that contains? What is this blue set formed by the trajectories of the vector field that converge to this point, to this saddle point? What happens that this is a smooth disk, and this is one of the most technical results of the paper, because it happens that the Hessian of the vector field at this point, or this would be the rescale vector field, the Hessian is degenerate. So meaning the Hessian here means that the matrix of partial derivatives of the vector field. So we use the theory of central stables of manifolds by Al-Kelly, which bypasses in some cases this problem. So our hope originally was like, okay, maybe we need to perturb the metric a little bit more, and we would get something that is non-degenerate, and we can apply Grobman-Harman, and that's it. We just get for free that this is a nice disk. But this is not the case. Like, it doesn't matter how you perturb the metric. This Hessian is degenerate. So this theory allows you, in certain situations that apply really nicely to our case, to also conclude that you have a smooth manifold of trajectories that converge to that point. Okay, so we have that on one hand, and now let's see what happens. I described the vector field on the interior parts. Let's see what happens between the intersection of two divisors, or the intersection circles between two divisors. So there are two cases. If you take two divisors in such a way that var pi I and var pi j is equal to 0, this is the model that you have near the intersection. So you have to imagine that this is a circle. Okay, so this side is glued to this side. So this is just a small neighborhood near one of the circles in the intersection. So in the intersection points. So this is a collection of these joint circles. Okay, and this is the model when var pi I and var pi j is equal to 0. And if one of them is not 0, this is the model that you have. On one hand, you have these half saddle points, and on the other hand, you have these half fountains and half sinks. And we are able to, so a determinant that is cooked with these numbers, var pi I, var pi j, and another element of the another of the numerical magnets that I put before, computes how many of these points appear exactly. So we have now a very good description of the vector field. We know that we can compute these numbers very easily, so we can compute the vector field near the corners, and we can compute the strict transform of the polar curve and see if it passes or not through that divisor. If it passes, it will acquire a saddle point, and if not, we will have a vector field that does not vanish on the interior of those pieces. So now let's see how this leads to the two main results that are in our work, and then maybe conclude with what is the future work. So first, we have a decomposition theorem for S theta. So we fix an angle, and we consider the set of separatrices that lie over the ray of angle theta. So we just see what are the we consider the set of separatrices, and it is easy to see that these sets are tangent to the image of the ray over angle theta by f. So this set makes sense. So this is and we by our result, the result that I just explained, this set decomposes into a disjoint union of finally many smooth disks. So these correspond to the polar points, the points of where the polar curve intersected the divisors, and certain intervals that correspond to fountains in D0. The fountains only appear in the first divisor. So this is first divisor is special in many senses. And we have an analogous, of course, decomposition theorem for S. The set of separatrices decomposes into a disjoint union, finally many open solid tori, which obviously correspond with this smooth disk, and annuli, corresponding to fountains in D0. So we have that on one hand. And now we can do the following game. So if you remember, I did this picture of the cylinder of the Morse singularity, and I said, take the stable manifolds and follow them backwards. And we got to a circle. So here we can do the same. So imagine that we have the Miller fiber that I drew before, and there was a polar curve passing through the divisor corresponding to that point, and it just happens that the multiplicity of the function f over here is 8. So because there was one intersection point of the polar curve, now there are 8 saddle points. So here we have 1, 2, 3, 4, 5, 6, 7, 8. And we follow the stable manifolds of those 8 points, and we follow them backwards, and modulo given some rules of what to do when you cross, so this is explained in the paper, you get always to some fountain on the first divisor, except for like some particular cases that just happens for a free moment, for a theta, in which you can hit another saddle point maybe. Okay, so here you have to think that this line 1, 2, 3 saddle point, and if you follow it backwards, maybe it hits the unstable manifold on another saddle point. So you can construct this set, and now we have the following result, which is this. First, a little lemma. We can contract all the connected components of the Miller fiber. So the connected components d rho I theta, where var pi is different from 0. And it just happens that the union of these pieces is this union of disks. So we contrast each of them in this picture. It would be the following. So these are var pi I for this is 0, for here is 0, and for these two is different from 0. And we see that the union of these is for this. So we can contract all these pieces, and we obtain something that is homeomorphic to the Miller fiber. Okay, so we do that operation. We obtain this. I contracted the two things that were on the right. And the theorem now says the following. So if we take the union of these stable manifolds that arrive at the saddle points, we contract this disk, then this is a spine for the invariant Miller fiber. So for the Miller fiber resultant after of contracting this disk. And the vector field on this space, except on the first divisor, which is special, is an analytical invariant. So this does not depend on the metric. So here in this picture, all the lines that are here, and actually in this particular picture, everything that you see is an analytical invariant of the singularity. And that does not depend on the chosen metric. And so if we do this operation fiber-wise, we obtain a Miller fibration. We obtain something that is homeomorphic to the Miller fibration that we call So this is the map resulting from contracting here all these disks. And this fibration admits a unique smooth structure compatible with the smooth structure of all these pieces. And this is equivalent to the Miller fibration as a smooth fibration. So we can work at this space, and each of the fibers of this space has a spine that does not depend on the chosen metric. And well, future work is like study Miller fiber at positive radius. Sorry, the spine at positive radius. Understand better the monodromy from the study of the set S, and also study what is the picture in high dimensional cases. So thank you.
Questions? We started a bit late, but I guess we can have some questions. Pepe.
Definitely yes. Like for example, I mean this is not. So for example, we definitely know that we can extend the vector field in higher dimensions. So far we haven't found a real theoretical obstruction, and also we don't think that there is any big piece of the theory missing. So what it's missing is acquisition of some technical tools on our side. For example, really understand the resolution process in higher dimensions. This is going to be play a big role. So here the resolution process is easy, and not only is easy, but two devices are intersecting in 1 point. In higher dimensions, this is much more complicated. Yeah, I understand the question. The answer is like we hope it does apply. The proof is going to be much more difficult. But we do know so far how to do certain things. But certainly we are not close to finishing the program in higher dimensions. We are close to finishing the program in the case of Plankers for these 2 points. Spine of positive radius and understanding the monodromy from these spines.
What happens along the new constant side?
So one thing that I didn't say is the following. This spine, as I said, this spine is an analytical invariant. There is an obstruction. So let's think about the spine over a circle, or over all the fibers at radius 0. In this particular case, the spine has the same homomorphism type for all fibers. But in general, this is not possible. There is an obstruction. The topology of the spine changes. So even if you stay in you look at the Miller fibration of one singularity, not even changing along the constant stratum, the topology of the spine already changes, and there is obstructions for it to be fixed, because if the topological type wouldn't change, the monodromy would be periodic, and we know that the monodromies of plane core singularities are in general not periodic. So we don't know what happens along the constant stratum, but certainly the spine is going to change. So if another part of the program that we want to carry away is the following. You take the versal deformation space, you take one fiber, and now you degenerate to several points and see what spines appear with this construction when you degenerate to several points.
Okay.
So then, for example, so in the curve case, you can break the Milnor fiber into pieces which looks like quasi-homogeneous.
Yes.
Would it apply?
Sorry?
I mean, would it useful to study separately for each, I mean, for what?
So you mean here we have this species where the monodromy acts? Yeah, so one thing that we are doing now is studying the monodromy. So the monodromy should be ideally understood as to what happens in each of these species and also understand the gluing between the pieces. So I don't think that that particular point of view adds a lot of to what is already known, because this is very classical theory. You understand the periodic monodromy in each of these species, and then you have some fractional numbers that are between these, and that you have to. We do expect to obtain something different, some decomposition of the action of the monodromy on homology that is given by the existence of this particular graphs. So some nice decomposition. What we are working on is to produce a basis of the homology that is naturally given by this spine. So recall the following: you take a saddle point, and I said that if you take a saddle point, you follow the stable manifolds backwards, and generically you're going to arrive to a fountain in the first divisor. So this almost defines for you a cycle canonically. Maybe you have to do something in the first divisor because you don't arrive to the same repeller, but you have a way of deciding a basis for the homology, and maybe this is in the direction we are working.
And maybe following, maybe in the case of quasi-ordinary singularities in higher dimension, where
that's,
I mean, it's
that's certainly a good case to try first. Yes.
Okay, thank you. We have no more questions. We are a little bit late. Should we have a small recess or small break, or continue with the full? 5 minute break. 5 minute breaks. Okay, we have a 5 minute break. Bueno, vamos a tratar de empezar. Ya pasaron los 5 minutos. Our next speaker is Benoit Gerville-Ballet, in joint work with Juan Viu Sos, and the title is Combinatorial Study of the Modular Space of Line Arrangements. Benoit is a freelance researcher for the moment, and
okay.
Begin.
Okay, sure. Thanks for the introduction, and also thanks to the organizer for the invitation and to give me this pleasure to talk today in front of you, and especially Kike and Alex for their birthday. And so I made my PhD with Vincent Florenz and Kike Hartal. And during my PhD, I studied topology of line arrangement. It was related to the talk of Vincent this morning. And after that, I studied a lot of Zariski pairs. And each time I try to construct new type of Zariski pairs. And to do so, you need to find arrangement with the same combinatorics, which are different. And after some time, I just realized that not the most difficult, but a difficult part is to find the proper example, to be able to construct the example. And also when I discussed with other people working with line arrangement or hyperplane arrangement, usually the question is, if you have this property, is it determined by the combinatorics, the intersection lattice or whatever? And so after that, I started to think, okay, maybe I should try to understand better the moduli space, to be able to construct explicit arrangement, to have the equation, etc. And this was the beginning of this study of the moduli space. So I will start with some basic definition, and the first one will be really related with the talk of Vincent this morning, because it's the definition of line combinatorics. He called it just combinatorics. I called it abstract line combinatorics, but it's just a set, a finite set, which is just line, P, which is subset of the power set, which look like the singular point, and some condition just to mimic the incident structure. And I called it abstract because some of them maybe they can have no realization. There is no arrangement with such combinatorics. So that's why I'm calling them abstract. And when we have a line arrangement, of course, we have a combinatorics associated, which is basically this set, which is just horrible when it's written like that, but it's just the information of which line intersect which other. So forget about this, it's not very important. Just remember that combinatorics is just information of which line intersect which other in double point, triple point, quadruple point, etc. So from this, we can define the realizations. It is very difficult to say. The space of realization of a combinatorics. And it is just a set of all the arrangement sharing the same combinatorics. And of course, when we have an arrangement, we can apply a projective transformation. And this projective transformation would transform your first arrangement into another one. And of course, they will have the same combinatorics. And so there is this action of the projective linear group. So we can consider the quotient of this set of space of realization by this action of the projective linear group. And that's what we call the moduli space. And that's much easier to say, moduli space. So also just to fix some notation, when we are using the realization space or the moduli space of the combinatorics of an arrangement, I will probably say just the moduli space of the arrangement, but you will understand, I guess. To have a look on what look like this space of realization, let's recall this very basic property. If you have arrangement line Li with equation aix plus biy plus ciz equals 0, then three line Li, Lj, Lk intersect in a singular point if and only if this determinant is 0. So that is, we only have algebraic condition. And of course, this is an equivalence. These three lines do not intersect in a point if this one is different from 0. Which means that we can define this realization space as just these are lines. We have that all the lines are different. We do not allow line to collapse. There is no multi-arrangement or something like that. So all the lines are different. This delta Ajk will impose some collinearities, some concurrences, and this one will avoid unwanted singular point. And so Vincent this morning also speak very, very quickly about ordered arrangements. And here I will be a little bit more careful on the definition. So an ordered arrangement is just an arrangement on which we fix an order on the set of the line. So this is one of the way to define this order. And very oftenly we consider the order given by the indices of the line. Sometimes we can take another one, but if I do not precise which order we are considering, just consider that it's the indices. And from such an order arrangement, we can consider this chain of ascending, of growing order arrangement. So we start with the smallest line, smallest in the sense of the order above. And so we start with this line. Then we consider the arrangement formed by two lines, L1 and L2, and then by three lines, L1, L2, L3, etc., until we reach the entire arrangement A. And so for such a chain, we define the tau I, which I don't like this way to introduce it. It's not the better way. Because it's something very intuitive, and we will see just after on the slide. But basically, it's if you consider the arrangement AI, is just count how many multiple point there is on the line Li, and by multiple point I mean point of multiplicity at least 3. I don't count double point. So yeah, let's have an example. So yeah, here first I define the type of an arrangement, and it's just the sequence of all these to I. So let's start with an arrangement. So just first line. So the tau 1 is 0. There is no multiple point here. Easy. Second one, there is one multiple point at infinity because we are in the complex projective plane, but it's just a double point. So again, tau 2 is 0. So still quite easy. Then we can add a third one. Once again, nothing new. A fourth one. So here we have 1, 2, 3, 4, 0. Now something begin to be more interesting, and I can add one diagonal. If you look at these diagonals, it passes through 2 points of multiplicity 3. So tau 5 is 2 here. I can consider also that one, which passes through these 2 multiple points. So tau 6 is 2. Then I can also consider one line passing just through one multiple point. So that's a line inside the pencil. And so that one we have tau 7, which is 1. And let's consider this last one, which is L8. It passed through this multiple point here, this one, and the one here far away at the infinity. And so that time we have tau 8, which is 3. So basically it's something very easy. You just add line and see how many multiple point there is on this new line. Yeah, just to a way I have to think about it. It's I don't know if you know this game, the Mikado or the pickup stick. You know, where you have some sticks and you put them randomly on the table, and you have to remove one by one all the sticks. In fact, you can think of this exactly in the same way. So here you start with your arrangement completely done like that. And I will say, okay, the first I want to remove is L8. And it has 8 points of contact. That is, it has 3 points of contact. That is the 3 multiple point. So that's a little bit difficult to remove. And then I have removed L8 like that. And then I can remove L7. L7 that time has just 1 point of contact, easy one. So I can remove it, etc., until to reach to the empty arrangement. So you can think it in one way to construct the arrangement piece by line, or to deconstruct it, removing line one after the other. So that's how my brain is working, just playing Mikado all the day. So now I will start to show you a list of different families of combinatorial families. So that is families of arrangement determined by the combinatorics, for which we know that the moduli space is connected. Oh no, sorry, I forgot this slide before. Yeah, so sorry. Just few more word about this. We have this relation between the tau I and the usual data of the combinatorics. If we have a look on this part of the equation, it's a kind of a way to try to guess the dimension of the space of realization. The first part here is the number of line times 2, because for each line you have 2 parameters to choose your line. So this is all the, let's say, degree of freedom that you have. And this is all the restriction imposed by the intersection point, by the triple point, etc. Because if you have just a double point, there is no restriction. If you have a triple point, there is one restriction, etc., etc. And so this is another way to think about it. You start just by counting. If you had a line passing through no singular point, then you have 2 degrees of freedom. That's exactly 2 minus 0. If it passes through 1 point, you have 1 degree of freedom. So it's 2 minus 1. If it passes through 2 points, you have no choice for this line. So this term is 0. And if it passes through 3 points, then now you have a kind of restriction. You need to make this 3 point collinear to be able to add this line. So you lose 1 degree of freedom. So it's just 2 different ways to think about how to construct line arrangements. Yeah. This is just a first try. Yeah. And that's the second point. I call this the naive dimension of the moduli space. And there is this -8 to fix the square by the action of the projective linear group. But this naive dimension is the first naive way to think about this dimension. And yeah, finally we have this relation between the naive dimension and the actual dimension of the moduli space. And of course, you all know the Pappus arrangement. I hope you all know. But for sure, all of you have already seen the Pappus theorem, and so you can guess what is the Pappus arrangement. And for Pappus arrangement, you have a kind of free collinearity between some point. And then this makes this inequality strict. And so that's why I call this naive dimension. It's the first approach, it's the first approximation, let's say a combinatorial approximation of the dimension of the moduli space. But as we can see with the Pappus, it's not fully correct. So yeah, now I start with families of arrangement with connected moduli space. And the first one was introduced by Nasir and Yoshinaga. And it is called the inductively connected arrangement. So an arrangement is inductively connected if you can just add line step by step without tau I bigger than 2. So that you never have to put point collinearly, so you don't have any restriction. And so just to have an example, I start with this 4 line in a square. That's the 4, 0 we have here. Then we can add this one. We have no choice, but we have no restriction. we can add this one, still no choice, no restriction, and we can add this one, just 1 point, and so 1 parameter possible. And so we have the type of the arrangement which verifies this condition here. So let me also introduce this two family, because I will need it in the future. So the first is the family of arrangement which form a pencil of n line. That's that type of arrangement. And the second one is almost a pencil, but with one generic line. And so we call them X and X bar. Just to remember, we choose this specific font such that it looks like a pencil, a kind of. And this one with a bar is just to say that there is an additional generic line. So it's a good way to remember what they mean. And so the result of Nasir and Yoshinaga about this inductively connected arrangement is that their moduli space is isomorphic to a Zariski open subset of an affine complex space of dimension, exactly the naive dimension. And so we can deduce from that that the moduli space is connected and that its dimension is exactly the naive dimension. For this one, naive dimension and dimension correspond. So yeah, let's introduce these two other families of arrangements. So the class of nice arrangement and simple arrangements, introduced by Yang and Yo for the first one and Wang and Yo for the second one. And what they prove is that if an arrangement is nice or simple, then the moduli space is connected. And in fact, in their paper, Nasir and Yoshinaga question in their introduction the relation between this class and the class of inductively connected arrangement. And what we prove with Juan is that, in fact, any nice arrangement or simple arrangement is inductively connected. So, in a sense, we kind of homogenized these three classes in a single one. Okay, let's continue with another class of arrangement with connected moduli space. And this one is a kind of, I will say, antagonist from the inductively connected. For the inductively connected, we had line each time with no condition, with no choice, with no collinearity, with nothing to force. Here we have that at each step there is no freedom, nothing. So we can add line through 2 points to 3 points, etc. at each step. And what we can prove is that this condition, which look like a geometric condition, is in fact, because of this proposition, a combinatorial condition. And so, of course, because of this condition, this means that the moduli space of A is just a single point, and so it is connected. So just to have an idea of what such arrangement look like, let's start with, again, this square. And so we can, here we will need to add a lot of line to have something interesting, because for the first one, it will look like something inductively connected, but spoiler, this tree will play an important role. So we can add first this line through the 2 point at infinity here. And so we have to I to 5, which is 2. We can add this line still through 2 singular point. This one, again, 2 singular point here and here. This one, which pass through this one, and the intersection of L7 and L5. So still no choice here. That one, which is pass through this one of this one. But the last one will pass through the point at infinity far away here, this singular point, and that one. These one are always collinear. There is no other possibilities as soon as we have made this construction before. And so we can add this line. And so we know very directly that this arrangement has a connected moduli space. And this arrangement is not inductively connected, for example, because if you have a look on all the line contain at least 3 multiple points. So when you will remove the first one, for sure the last to I will be at least 3, so it cannot be inductively connected. So yeah, this is something way more rigid than the inductively connected. That's the name, inductively rigid. So yeah, that's another possible class, combinatorially determined again. So no need to study equation deeply to know that moduli space is connected. Again, in their paper, Nasir and Yoshinaga introduced a last class which is called the C3 simple. So first, what is the class of C3 arrangement, of CK arrangement? CK arrangement is just arrangement for which all the multiple points are contained in a subset of K line, with K as small as possible. So for example, if all your singular multiple points are on one line, then you are C1. If all of them are on just two lines, you have C2. And the first result is if A is C0, C1, and C2, then the moduli space is connected. When you arrive to C3, problem begins. For example, MacLane arrangements, we know that there is two connected component is C3. So we don't have the following any C3 arrangement has a connected moduli space. But Nasir and Yoshinaga introduced a subclass, which is a class of C3 of simple type. So this simple has nothing to see with the simple before. So sorry, Masahiko, but this choice of name was maybe not the better. But we understand what it means. It's a very more simple class of C3 arrangement. And so this class is two particular possibilities for C3. The first one is the three line containing all the multiple points are in generic position, but for one of them, there is just one multiple point on it. The other possibility is that the three line containing all the multiple points are collinear. And what they prove is that if an arrangement is C3 of simple type, then the moduli space is connected. And in fact, when we looked on the proof of this result, we realized that there was something possible to do to make this class bigger and to allow arrangement of class C4, for example. And that's what we did. We defined the class of arrangement which has a rigid K-pencil form. So such arrangement contain a subarrangement A prime. We ask that this subarrangement is inductively rigid, so that that's a combinatorial condition. Then we have that this A prime contain a singular point, a multiple point of multiplicity K. And then we ask that for any multiple point of the arrangement A, we have either there is two lines of A prime of this inductively rigid arrangement passing through this singular point, or that the singular point is on the pencil formed by P0. So I will give you, maybe I can just show you this example before. So this is an inductively rigid arrangement. That's A prime, because you can start again with a square, add the two diagonals, and this one, and each time you have no choice. So it's inductively rigid. And so we will consider A prime this one, and P0, which will be the point at infinity here, between L3, L4, and L5. And we add three lines. So the first one is this one, passing through this singular point. Then we take the parallel passing through that one, so we create another multiple point here at infinity. And a last one like that. This one passed through this point, and this point. And so if you have a look on this one, on this arrangement, so multiple point, there is some of the line at infinity, that is the intersection here, the one here of this one, and P0, of course. Then you have this one, and this one, which are on L4, this one, and this one on L3. That's almost all the multiple points. There is another one, which is there. And this one is not in the pencil, but it contains two lines of the inductively rigid arrangement. And so what we proved with Juan is that if an arrangement has a rigid K-pencil form, then its moduli space is connected again. And this proposition shows that this class of this combinatorial class of arrangement generalized the class of C3 of simple type. And so this allows to have multiple points or more than just 3 lines. So if we have a look on this one, no, this one, yeah. All the multiple points are on the 4 line passing through the center here. And so this one is a C4 arrangement. So it's a way to allow to increase the class of C3 of simple type. So that's all for the class with connected moduli space. Now we'll shift to something else to try to guess how many connected component has the moduli space of a combinatorics, of an arrangement. And for that we introduce first the notion of elementary perturbation of a combinatorics. So basically it's just to move a line out of a singular point. So we describe it in a more abstract way, but just remember this. You have a singular point and you just move one line out of this singular point. And then we define the notion of M perturbation, which is a sequence of M elementary perturbation. And we ask one condition is that the last one of the sequence is inductively connected. Of course, it comes with an associated order to prove, but that's not very important. And we denote such M perturbation like that, so with 2 preceding symbols. And what we prove is that if we have an arrangement A, which is different of these 2, that is the pencil and the pencil plus 1 line, and which admit an M perturbation, then we denote also D0 the naive dimension of the moduli space of C0, which is the last element of the M perturbation. Then we have a Zariski open subset W0 of an affine complex subspace of dimension D0 and M polynomial delta 1 to delta M, such that the moduli space is isomorphic to this space. And basically all this condition is the one we create when we move the line outside. So we remove one condition to allow something more flexible, but finally we impose them later. And so from this result we obtain that the delta, the difference between the actual dimension of the moduli space and the combinatorial approximation, the naive dimension, is smaller than M. And it tells you how much far you can be, how big can be your mistake. And here we find we find again the result saying that if an arrangement is inductively connected, then the moduli space are the same. Because if an arrangement is inductively connected, then you don't need to make any perturbation to have something inductively connected. So you have a 0 perturbation. And so here you have that this difference is 0. So from this construction, we can, from the construction we made from inductively connected arrangement by adding lines step by step, we can keep track on how complicated are the coefficients of each line, because they will depend on some parameter, and all the coefficients at the end will be just polynomial in this parameter. And what we want to do, and what we will do, is to keep track on an upper bound on the degree of each coefficient of the line, of each line. And to do so, we take this, we define 2 maps, A and I. The first go from the set of line and the second from the set of point. And in fact, these 2 maps will just track, they will encode an upper bound for the degree for this one of the coefficient of the line, of each line, and for this one, for the maximal degree of the term of the coordinate of each singular point. And so first, this will be done recursively. So we will first fix the square as usual. Since it's fixed, so there is no parameter here, so everything is fixed with 0. The singular point of this square, again, points are fixed. Value is 0. And now things begin. If we had a generic line, then it will be linear in 2 parameters. So linear in 2 parameters with degree smaller than 1. So that's why we associated 1 when the line is generic. When the lines pass through just one singular point, you have 1 degree of freedom, which is the one here, but it also depends on the coordinate of the point P. And so this gives you an upper bound on the coefficient of the line Li when it passes through just one singular point. And here it's the same when it passes through 2 singular points. And we don't have something with more singular point because we are working right now with C0, which is inductively connected. And so when it's inductively connected, all the tau I are smaller than 2, so you cannot have something else than these 3 cases. Okay? And now, when we had new line, it passed through some multiple point, but it also creates some new double point. And so now we can compute an upper bound for the degree of the coordinate of this new double point. And that's exactly what we are doing here. So it just depends on the 2 lines intersecting, the 2 new lines. And finally, what we obtain is that the number of connected components of the moduli space is bound by this. So we take the product on each step of the M perturbation, and this just bound the degree of the delta of the condition imposed by to bring back the line we move out of the singular point. So this allows us to have a bound which is quite correct. Let's give this example. I'm sorry, this slide is very dense. Sorry, Patrick, for that. So this is just MacLane combinatorics. You don't need to read everything. And we can make one elementary perturbation on L8 at this point. That is exactly this point here. And all the rest will be the same. But this point, when you have a triple point and you move one line out, this point, you get 3 double point. That is this point here, this one, and this one. But on this combinatorics, we can check that the type of this combinatorics is this. So it is inductively connected. And then we have one permutation, one perturbation. In particular, just to say it there, this means that the moduli space of the MacLane arrangement is of dimension smaller than 1. And so we can compute the value of the map A. So of course, for the first 4 lines, there is nothing because that's just the square. The 5th line is the line at infinity. It passed through 2 points, so there is still nothing. Then we had one line through one singular point, and so this one has just one parameter. It is linear in the parameter, so its maximal degree is 1. And then when we construct all the other, again, it is constructed in such a way that each line is just linear in this parameter. So we obtain just one for each, for the 3 last line. And then we obtain that the MacLane arrangement has at most 2 connected components because A4 is 0, L6 is 1, and L8 is 1. And that's exactly the point we have here, and that we on which we make a perturbation. And so like that, we obtain that we have at most 2 connected components, and that's exactly the case for the MacLane arrangement. So that's all for this presentation. But since we are here for these 2 great mathematicians, I just would like to share one story I had with Kike that I really loved, and that will show you how much he can share with his student. And in fact, some years ago with Juan, we found a new example of the Zariski pair of real complexified arrangement. We were really proud of that, and we just sent the equation of this arrangement to Kike so that he can have a look on it. And so that's what he did. That's what he did. And in fact, this same year, few days after we sent it, it was Christmas. And for us, it played like Santa, because exactly the morning of Christmas, the 25th of December, I just received, and Juan too, we both received an email just written, the fundamental group are different. So even the day of Christmas, he was still working. And so it was a perfect present for us for Christmas, and thank you for that. It's just a memory for me, amazing. So yeah, I will stop on this small anecdote, and thank you again, and as I said, happy birthday to you too. So, thank you.
Questions?
Your example in the thesis is falls into the last category.
Sorry?
Your example of the combinatorics which had four
The C4. Oh yeah, for this one, yeah. Again, the bound is a good one. It's exactly 4. In fact, for all the example the usual example of the risky pair with 4 connected components, for all of these ones, they have a kind of similar combinatorial structure behind, and each time the bound is a good one. It's 4. I also computed for I computed for several for MacLane, not for MacLane, for Rybnikov. There is a difference. I didn't succeed to make it smaller, but yes, for Rybnikov, I think it says that there is 8, at most 8 connected components. There is a factor 2 appearing here, and I couldn't yet remove it. For yours a risky pair, there is also something particular because the naive dimension is negative, and that's something particular. And in this case, we can in a way adapt the last theorem by removing the smallest term, and in that case also this predicts that there is 2 connected components. Without this amelioration, it says that there is 4.
For the moduli space, what do you expect to have?
For the moduli space of which? Of what? Of
You could maybe give a closed formula for it, or
sorry. Yeah.
A closed formula for it, or not? For the dimension.
For the dimension is way more difficult because of the Mnev universality theorem, for example. It says that any type of singularity can appear in the moduli space of a line arrangement, and it makes it quite difficult to guess what is the dimension, and we have no idea how to handle it better than just saying that we can estimate the mistake we are doing between the naive dimension and the actual dimension, but we didn't succeed yet to have something better than this.
So you can define this modular realization space for curves.
Yes.
So for example, there are examples in quintics, even related with some Terao conjecture, where the modular space is a Sierpinski. So it's 2 points, but I mean not a discrete space. So can it happen in line arrangements for combinatories that the moduli is not a Hausdorff space, or?
That's a good question. I don't think it's possible, but again, I will be careful because of Mnev universality theorem.
Maybe Masahiko knows.
Yeah. By the way, if anyone here knows about Mnev universality theorem, I will be happy to discuss with him. So that's just to say. Okay.
Any other questions?
Patrick.
Patrick.
So Mnev universality theorem, if I'm right, already applied for line arrangement, for complex line arrangements. So, I mean, from what I understand about all the different type of naive universality theorem, there is naive universality theorem for oriented matroid, for scheme, for a lot of different objects, and from what I understand of all of them, I think it fits also for line arrangement, but I'm not fully convinced by the proof of this theorem. So that's why I'm looking for someone knowing it to discuss with him or her.
Okay, so we thank again the speaker.